everything that's projected on the board in sync. So you can go back and see any of this. Okay. Now, that's what I had you look at, or I thought I was having you look at for Thursday to see that first video for my first class last fall, okay, when I taught the same course. Of course, it was the older syllabus, but it was the same. I mean, very little changes, office hours, that kind of stuff. Research paper, the same, except for what months you get what points, okay? It's the same. Now the new stuff's out there and you can watch it. I mean, you can look at it on Blackboard, or you can listen to the video. The video is going to be talking about the previous term. The stuff that's out there under content, that's this term. Okay. Now, so you get all that list, playlist. Now, what you'll see, the older files are at the top and the newer files at the bottom, because it always loads from the bottom. So this will be the first one we've loaded this term, and it's going to be Chapter 14 or something like that, okay? And it will replace, I'm going to leave the syllabus one on there because that's the one you need to be looking at, because that's from last term, but then the new stuff will be at the bottom. So every time we have a class, I'll do that, and I'll delete the one that was equivalent to it at the top from last term. Okay, but I'm going to leave that syllabus from there. So that's the YouTube videos. Then after that is the research paper instructions. And I've gone over that in the YouTube video for syllabus from last term. You can hear me talk about it. And the only difference is the name of the months, you know, when you get bonus points. This term, you turn in your research paper in the month of January, you get 4 bonus. No, wait. In this class, it's 2 bonus points. In the month of February, you get 1 bonus point. And if you turn it in the first week of March, you just get that. Okay, so that's how you get bonus points. Okay, those are research paper instructions. Then you'll find all, okay, let me go over that. I put some some files out there that either students, generally ones that students have found and sent to me, I thought were really good. The first 10 of those, after the research paper instructions, okay, YouTube videos and research paper, are 10 incredibly pretty pictures taken by the Hubble Space Telescope. They're just really neat pictures. That's all they are, just images, but they're really pretty, okay? These are of stars exploding or nebula or other things we'll be talking about. Not those in particular, but you'll see the reference there. Then there's a file called Space Objects in Perspective. And a student found that and sent it to me one of the early times I taught the course. I thought it was so neat, I've included it in there every time. It shows real good relative sizes of Earth, the Moon, Mercury, Venus, and Mars. Earth is the largest of those, almost the same size as Venus. We'll talk about this in a later chapter. But then it shows the 4 gas giants, Jupiter, Saturn, Uranus, and Neptune, and Earth now becomes much smaller. Okay? Then it shows the Sun with these others compared to it, and now we're basically a single pixel on the page. Okay? We're that tiny compared to the size of the Sun. Then it shows the Sun in comparison to other stars. And it's incredible. There are some stars that make our Sun look like a little pixel on the page. So it's really a neat illustration of the relative sizes of all the things. And I don't know if any of you remember the old comedy show that was Third Rock from the Sun. We really aren't much of a rock. We're the third piece of dust from the Sun. I mean, we're that insignificant in the shape and the size of the universe. It's incredible. So anyway, space objects in perspective. And then after that, you'll see all the PowerPoints that we will possibly use this term. So you can see those. You can print them off if you want to take notes on. You can do nothing with them, whatever you want to do. Okay? So that's what's out there, and that's pretty much how it's located. Any questions on that? Please go to that first YouTube video, watch it and listen to it, and then look at the other things, and hopefully things will make sense. If you have any questions about any of it, bring it to me and ask me, okay? So, anything else that needs to be covered? Any questions on anything before we start on today? All right. Then today we'll be starting with, if I can get my fingers to work right, you'll probably hear me say this on the video if you listen, but I'll go on and say it now. This is Melanie, right? Okay. Okay. Just a little note. The big physical science book, you'll not find this one in the bookstore, you'll find them more like the sizes of what I see y'all have, okay? But the physical science book, and that one says on the cover, Dr. Charles Fowler. I did not write the book. I just told them what chapters to do for this course, and then they put my name on front. The author is Bill Tillery, okay? I think from Arizona State or somewhere. Okay. Just about every physical science book I've ever seen starts with physics and chemistry, and then goes into earth science and astronomy and earth science. Okay? And that's how it's put together, because the physics and chemistry, you really need that to really understand astronomy and later earth science, because those are built on the other two. But in the state of Alabama, okay, Physical Science 111 is astronomy and earth science. That starts in the middle of the book. And then Physical Science 2, if some of you have taken it, others of you might be planning to take it, that is physics and chemistry. Okay? So, believe it or not, the state of Alabama is a little backwards. Okay? I'm sorry, I didn't say that. Okay. So, anyway, that's why we're starting in chapter 14. Okay? And if you take Physical Science 2, then we'll start in chapter 1. Okay? So we'll do them in reverse order. So therefore, when we get to some of the examples in here, they'll be requiring you to solve some problems based on what you learned in physics and chemistry, but you haven't had physics and chemistry except maybe a couple of you, so we won't be doing some of those. I may go over them briefly, but we'll just basically ignore most of those. So anyway, we're starting with chapter 14. That's why we're starting here. And as I said, let me go from current slide. Okay. Something I was going to say on that. Oh, the two major topics here, general form, astronomy, that's chapters 14, 15, and 16. And then earth science, and that's basically geology type stuff, rocks and minerals, plate tectonics, building the earth's surface, eroding the earth's surface, that kind of stuff. Then we get into things like weather and climate, and then we get into Earth's waters, oceanography, just a little bit of that. So that's basically the course. Now, at the end of every chapter, we'll do a lab. And all but one of these, that lab is a paper lab that many of them came out of a lab book. I think in this class, just about all of them came out of a lab book. But I'll just run copies of them for you so you don't have to buy the book and then rip the pages out. So I'll run copies. Now those labs, okay, let's talk about the structure of the course first. In your schedule, it says the class meets 1:15 to 3:45. Second.
Is that true? 1:15 to 3:45?
Say that again.
Is that true? 1:15 to 3:45?
That's what it said, Jeff. Is that what you're asking?
Yeah, I mean.
Okay. That's when the class meets. Supposedly, the lab meets 3:45 to 5:45. Okay. Now, here's my theory of teaching in general, especially lab courses. I don't think it makes any sense to do the lab before you cover the material in class. So if we don't finish chapter 14 by 3:45 today, we're going to move on into the lab period and continue with Chapter 14. Now, we may finish it in time. If we do, then we'll go right into the lab and do the lab. But there will be days when we have a test. And here's how I like to do that. I like to do the test the very last 30 minutes of the class. Because the thing is, none of the tests in this class will really take you longer than that. But if they do, I can stay here later and be with you, but the rest of the students don't have to. So if we have a lab that same day, then that will be 2 hours before the test. So that will move into class time, which is fine. It's up to us to do. And that day, we won't have more than 2 hours of class, 2 hours of lab, and 30 minutes of test. Now, if we don't have a test one day, then we could go, say, 4 hours of class, and then 30 minutes of test. We do whatever it takes that makes sense. But always the test is the last. The lab may be the last if we don't have a test that day. If we do have a test, it'll be right before the test, and then the lecture part will be the very first one. And it may be 2 hours, it may be 2.5 hours, or it may be longer than 2.5 hours. Most of the time we'll pretty much set class, lab, and then maybe test, if there is a test that day. Okay. Now the reason I do that, I figure everybody needs to be here for class, and y'all are here, so we have class. Labs, if that's the last thing we're doing that day, if you finish early, you can leave. If we did lab at the beginning, then we'd have to wait till everybody finished, and then we'd start class, so y'all be sitting around, and then we go till 3:45. 5:45. So if this is what you're asking, this is what I do it this way, so that if you can leave early, you can. Okay. Yes.
So for the labs, if we have somewhere to be around that time period on a certain day, would we be able to do the labs on our own?
No. The labs we do, generally we do the labs in class. So let me go back to that. They're paper labs, and the first few we're going to do as a whole class. You'll each have things to do during some of them, but basically we're going to do as a whole class. The first two are like that. The third one starts off that way, but then part of its lab is going to be what you do at home. And you'll spend about 2 weeks finishing that lab, because that third chapter that we do, the chapter 16, is basically the Earth-Moon system. And it's called the Earth in Space, but it's the Earth-Moon system. So you're going to be observing the moon every other night for about 2 weeks, okay? And doing the shape, size, position of the moon at the same time. We'll go into that then. So that lab, to answer your question, that one you'll be somewhere doing that depending on how you want to do it, okay? Now, the fourth lab isn't associated with any single chapter. It's associated with the first 3 labs, the first 3 chapters. It is, if I can schedule it, it's a trip to the planetarium at Stanford University, okay? And we'll take most of that whole class period that day. So that day, the lab will be almost the whole day. I mean, we would have to drive there, be there, and drive back. We may have some time at the end to do something. We may have, depending on when he can take us there, we may have some time at the beginning we can do something. The general will be leaving right at 1:15 to get over there by 2 o'clock, and then be there for usually an hour, hour and a half, 2 hours, and then drive back, and that's most of the whole day. So that day we won't have, if we can schedule it. There's some terms I've not been able to schedule, mostly in the summer, because summer is like kind of crazy over there. They have lots of kid groups in there all the time, so it's hard to schedule. But usually fall and spring we're able to do that. So that is a special lab. It's an optional lab. You don't have to go. I can't force you to go on a field trip, but if you go, you get 25 points. If you don't, you don't get those 25 points. Okay, so it doesn't count against you, but the 25 counts for you. Okay, so let's get to how I do the grading in here, since that came up. Okay, this is a four credit hour course, right? 3 credit hours, those are called theory hours, and 1 hour is called lab hour. Okay, 3 out of 4 theory, 1 out of 4 lab. So I say the lab is a quarter of the grade. And since it's a quarter of the grade, I make all the labs worth 25 points. Not 100 points, 25 points. And therefore, at the end, average your labs together. You do get to drop your lowest lab. We'll talk about that in a minute, too. And the average of all the other labs will be something close to 25 points. Well, then I take all your test grade, the research paper that is not droppable. That's required for the course. Research paper. So please do it. Get started soon. Okay? And each of the tests. I think there's maybe 7 tests. Okay? And then there's the final exam. Okay? So the research paper, 7 tests, final exam. I drop the lowest of the chapter tests. Don't drop the paper. I don't drop the final exam. You don't want me to drop the final exam. That's a pretty easy test. Probably going to be one of your best scores. But that's required for everybody. So I drop your lowest test score if that helps your average. And then take 75% of that. And then that I add your lab average to. And that gives you your final grade. It's all explained in the syllabus. And you can go back and read that. Okay. So let's now talk about that optional lab, the bonus lab, I'll call it, the field trip to the planetarium at Stanford University. I do drop at least 1 lab score. If you go on that lab, you get your whole 25 points just for going. There's no paperwork, there's no, nothing that you can get marked off for. It's 25 points. Then at the end of the term, you get to drop 2, the one that was droppable and your next lowest one, because that one gets to replace it. Now, I said all but 1 chapter, we have a paper lab, okay? And I did mistake this. Yeah, the very last chapter, the oceanography, they didn't have a good lab with that in the lab manual, so I made up 1 there. So we do have 1 there. But for the weather and climate chapter, that's the next to the last chapter we do, there's nothing there, and it's sort of hard for me to make up something. So what we do for that lab is another field trip, if we can schedule it. Jerry Tracy goes to the same church that I do, so I know him, and I check with him, and he invites us to go, and he takes us through the Weather Center at Channel 13. So that will be the lab for that. So that's also, I can't force you to go on the field trip, so that's the second optional lab. If you go, you get 25 points, then you get to drop the next lowest lab. So if you go to both field trips, you get to drop the 3 lowest labs. If you go to just 1 field trip, you drop the 2. If you don't go to either field trip, you only get to drop 1 lab. And you get 25 points just for going. You don't have to turn in anything. Okay? Does that make sense? Okay. So pretty good ways to boost your lab average. Okay. So what we'll do is get started on chapter 14, get as far as we can today. If we finish the chapter today, now so much time has gone, we may not make it. But if we finish before 3:45, then we'll do the lab. Well, let me give you a little bit of history. Generally, this first lab lasts more than 2 hours. It's the only one that does, usually. So what we may do is when we finish the chapter, we may get started on the lab, and then next time finish the lab. And that way, you won't have to listen to me talk for 4.5 hours. Okay? Though you would love it, wouldn't you, Melanie? Yeah, oh, of course. I knew you said that. Okay. All right. Any questions? All right. So let's get started. And generally, we already would have been started because 4.5 hours on Thursday, last Thursday, we would have gotten further than just the stuff there. We would have already started on chapter 14. So we're already a little bit behind, so let's get moving. So, the 3 chapters on astronomy, chapter 14, 15, and 16, we'll start with the universe, everything. Then we'll narrow down to our solar system, that's chapter 15. Then we'll talk about the Earth-Moon system, that's chapter 16. And after that, we go to the planetarium, okay? And after that, chapter 2, you get the lab that you're going to be observing the moon for. But it's all in the handout, so we'll talk about that later. So we'll start with the universe. And each of these chapters has a core concept on the very first page. And this one is, the night sky is filled with billions of stars. The sun is just an ordinary star. It's ordinary in size, it's ordinary in temperature, it's ordinary in just about everything you could think. And it only has average brightness. Wait a minute. The sun's out there now. I don't see any other stars. And when the sun sets, then I see the stars. How are they brighter than the sun? At least half of them are brighter than the sun. Anyone have an idea?
We're close enough.
The sun is only 93 million miles away. Whoa, only 93 million miles? Well, guess what? The next closest star? Incredibly further than that. Okay? We'll talk about how far in a little bit. So we just have an average sun. Now, I bet you got there at night and you don't see a billion stars. It says billions of stars. Why? Why do you not see billions of stars? The night sky is filled with them.
Some clouds.
Say again?
Clouds.
Clouds, okay, that certainly could contribute, but on a perfectly clear night, you probably still aren't going to see a billions of stars. Why?
Maybe some of them are even farther than those.
Okay, yeah. But I'm just going to guess on this one, of where you live, since I'm guessing most of you live in a fairly populated area, possibly with street lamps, street lights, things like this. We have in town what they call light pollution. I grew up on a farm in Georgia, okay? And we were 8 miles from the closest flashing light, okay? 10 miles from the closest stoplight, okay? So we were way away from any light pollution. So when you looked at a clear sky at night there, you probably came close to seeing billions of stars. You couldn't identify each one, but there were just so many out there, you couldn't even pick them up. Here in town, no, you can't see that many because the competition of the light, okay? Now, a little anecdote here. When I was in college, freshman year, I was just in the dorms and living there. My sophomore year, at the end of my freshman year, I went to a little course, and applied and got hired as a student counselor in the dorm. Okay? So my sophomore year, I was a student counselor. My junior year, I had applied and got the senior counselor for that dorm. And that year, that was my junior year, a couple of guys moved into the floor that I had been a counselor on in the same dorm. And I got to know them fairly well. I went to Georgia Tech, so we had lots of students from other states. Max was from Boston, and Bob was from New York City. Okay. Both of them very dense metropolitan areas. All right. Now, my senior year, I started off still as a senior counselor in that dorm, but then I moved to be a resident advisor in another dorm, my last two quarters. But my younger brother was a freshman that year, and he was in the same dorm I started in, up on the same floor, the third floor, where I had been a counselor, and Bob and Max were still living on that floor. And he got to be pretty good friends with them. Now, because I was busy with the dorm job and Navy ROTC stuff and other things, and just busy with school, I didn't get to go home much. Dan, however, freshman, lots of things to study, he got to go home. He went home pretty frequently. Now, of course, he drove my car, okay? Little brothers do that. Oh, you wouldn't know about that, would you? Okay. Okay. And I've had two of his brothers in other classes, too. Currently have two and had all three of them in one class. So I know he had little brothers. Okay, but anyway, Dan got to be friends with Bob and Max, so he invited them home to the farm. It was the spring, and I certainly was busy at school, so they went on home. And by that time, my grandmother was living with my parents because she was in some memory loss type stuff and wasn't able to stay in her house. So Dan and Bob and Max went over to her house to stay outside of parental supervision. Now, whatever they may have been consuming that evening, perhaps contributed to this story. But most of it, I think, would have happened anyway. But it was a clear night, pleasant temperature, spring, and the field right next to my grandmother's house, remember I was on the farm, they had planted in soybeans, and they were probably not very tall at all by that point. And I don't know if Dan asked if they wanted to go outside. They just decided to go out, and they went out on this clear night, this guy from New York City and the guy from Boston, and looked up at the sky. We were 8 miles from the closest street lamp, okay? And they went nuts. They just went tearing through the soybean fields and, look at the stars! And, you know, they had never seen anywhere close to that many stars in their life. They probably had never seen the Milky Way, because in town that's just not even, you know, bright enough for you to distinguish it. And they saw them all. And they just went, Dan said it was the funniest thing, see these two guys just running across the field. Look at that, look at it, you know, and stuff. Because they were first time in their lives. Because Georgia Tech is in the middle of Atlanta. They had never seen the stars there either. First time they had ever seen anywhere close to billions of stars out there in glorious display, you know, in the sky. So, anyway, that's our core concept here. Boy, that took too long, didn't it? So let's talk about the night sky. That is the first topic in chapter 14, 14.1. Now, celestial observation dates back to the ancient civilizations. Okay? I mean, way back. I'm sure if we knew enough about the ancient civilizations, we'd know tons more than we do now. But the ones that fed into our culture, mostly the Greeks, okay, and to some extent the Egyptian, that the Greeks got from them, and possibly some of the others, Mesopotamia, the Sumerians, which are the ancient Babylonians, they, hey, you think we're pretty sharp now? They probably knew more about the night sky than we do. Why?
Light pollution.
Yes, they didn't have any light pollution. They could put out the campfire and that was all. You know, that's all they had. Yeah. So they could see them all. And what else?
They probably seen more stars before they blew up.
Second?
They probably seen more stars before they blew up.
Okay, one more time. My hearing's bad.
They probably seen more stars before they blew up.
Yes, okay. And what they did, they also, many times, lived outside. And guess what? They didn't have televisions. They didn't have radios. They didn't have cell phones. They didn't have any of this stuff. What did they do sitting around at night? They made up stories with the stars being the characters in the story. They named the constellations. Leo the lion, Taurus the bull. They used things from their mythologies. Perseus, who was a big, strong guy. Hercules, you know, and there were others, you know, kings and queens, either that existed or were mythological. And they knew them, and they knew their stories. And they watched them night after night. And they, as the year went along, at some time, Leo would be coming up at this and so time. Other times Leo would be over here. Other times you never see Leo, okay? But they knew them, and they knew by looking at them which ones were what. And after a while, they knew when this star came up the first time, that's when you probably should plant your barley, okay? Because it happened very regularly. And when this star disappeared, you better start harvesting your corn, you know, or whatever it happened to be. They knew, this is how they knew the times of year, the seasons and everything else, because they knew that night sky. And they made observations because they lived it. Okay? We'll talk about some other things they did with it too. Now, let's talk about what they saw in the night sky and what we see. We see stars. Now, what are stars? Anyone know? We say twinkle, twinkle, little star, but you know, they really don't twinkle. Maybe a couple of them do kind of, but they really don't. It's the interference of our atmosphere that makes them look like they twinkle, okay? So they really don't. They actually appear as point sources. No matter how big that star is, it's so stinking far away, except for our sun, of course, except for the sun. Now, you don't see that at night. This is night sky, okay? They appear as just a single point. Now, some of them are brighter points, some of them are less bright. But even if you got the most powerful telescope you could do and took a picture of that star or looked at that star, it would still be just a point of light. You wouldn't see any shape to it other than being a point of light. So that's what they mean, appear as point sources. They twinkle because of our atmosphere's turbulence. It's nothing to do with them. Now, we said the sun is only 93 million miles away. How far are these stars? We don't measure it in miles. The numbers are just too big. Okay, 93 million sounds like a big number? Okay. Here's what we measure it in. We measure it in light years. Does that sound like a distance measurement? Sounds like a time measurement. That's what years are, right? No, this is a distance measurement. And here's what we mean by it. Does anyone know, is light instantaneous? No. It seems like it is, but it really isn't. Light has a finite speed. Anyone know what it is? 186,000 miles each second. That's close enough to instantaneous for me, okay? But that is instantaneous. The 186,000 miles it travels in 1 single second. Now, if you could picture the Earth here, and let's go around the equator of the Earth. If you could shine a flash of light, okay, and get it to travel in a circle rather than a straight line, if you could do that, and did that, just do a flash, it would go completely around the Earth 4.5 times in 1 second. That's how fast light travels. Pretty fast. Okay? That's in a second. Okay? Multiply that by 60, 186,000 miles times 60, that's how far it travels in a minute. Multiply that by 60, and that's how far it travels in an hour. Multiply that by 24, and that's how far it travels in a day. Multiply that by 365 and a quarter, and that's how far light travels in a year. That's a long way. That is a long, long way. That happens to be 9.5 times 10 to the 12th kilometers. Well, multiply that by 0.6, and that would be about 6 times 10 to the 12th. 5.8, 5.9, something like that, times 10 to the 12th. Okay, how much is that? This is miles now. That would be, let's call it 6. 6, comma, 0, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0. That many miles is how far it travels in a year. That's a long way, okay? The first 3 zeros are thousands. Next 3 zeros are million. Next 3 zeros are billions. That's trillion. About 6 trillion miles. 6 trillion miles in a year. That's 1 light year. That's how we measure distance to the nearest star. How far is it to not the sun. Sun is only 93 million miles away. The nearest star is multiple light years away. Multiple light years away. The distance across our galaxy, just our galaxy, the Milky Way, 100,000 light years. Okay? Now what this means, look out there, pick a star, your favorite star. It's so far away that that light that you see that just entered your eye from that star, let's say that star, pick a number, something between 10 and 100,000. Pick a number. 200,000, okay? No, okay. 20,000. 20,000, okay? Let's pick a number, 20,000. Let's say that star is 20 20,000 light years away. You're looking at it. Probably a pretty dim star because it's so far away. Guess what? The light that you're seeing coming through your eye right now left that star 20,000 years ago. Meaning that star may have blown up since then. It may be that what you're looking now doesn't exist there anymore. But it took that long for it to get here. That's what we mean by light year. Incredible. Okay? Enterprise to start to mission control, or what do they call it? Whatever it was on Star Trek. They couldn't talk to each other. It would have taken years. If they were galaxies away, it would have been lifetimes away before they got an answer, because radio waves travel at the speed of light. And it was 20,000 miles away. Been 20,000 light years away. Been 20,000 years before they ever got the message. And then they answer, you've been dead. Okay? So no, this is science fiction. That was. Now, other things we see out there, not many of these, but planets. Okay, by the way, let's go back to stars. Stars, the light you see is from that star. Okay? That star is manufacturing light, just like our sun is manufacturing light. The light you see from the planets, not manufactured by that planet. That's the light from the sun reflecting off the planet back to us here. Those are dark, dim chunks out there. They're not emitting light just like the Earth is not emitting light. If you look at the Earth from space, you see light reflected off the sun. Okay? When you look at the moon, you're not seeing any light coming from the moon. You're seeing light from the sun that's reflecting off the moon, and we see it here. And that's why sometimes it's just a little sliver, because there's only that portion of the moon is facing the sun. The other part you don't see. That's facing the sun. You just see this little sliver. Okay? Or it's a full moon. It's here, and the sun's back here. You see all of that face of the moon. Okay? So the planets are visible only by reflected light, and they are extended sources. Now, what do we mean by that? You get your telescope and look at a planet, they are so close, you can actually see the shape of the planet. You can see the circular thing. You can see some of the moons of some of those planets, okay, besides our moon. And you see they actually have dimension to them. A star, no matter how powerful the telescope is so far away it still looks like a point of light. And that's all. Okay, now we're going back to the first bullet here. Does anyone know what this is? Anyone? Stonehenge. Stonehenge. You know where it's located? England. Okay? Now, do you know who built it? Who? Nobody knows. It was there long before the earliest civilization that we ever knew was living on England. It was already there. Okay? Is that something that was nature-made? No. This is man-made. By some civilization way, 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 way before we knew anything about that civilization. We don't know who built it or how they built it. Now here's some incredible things. Now, I'm trying to find, I think that little thing right there is a person. I know this is one. Here's a person over here, okay? This is an incredibly huge set of rocks here. Those rocks did not come from the local area. They came from a long way away. Now, how in the world did that ancient of a civilization transport that big of stones, these bigger rocks, to this place? I don't know. But I'm sure they did somehow. Next question. How did they get them to stand up? This is an ancient civilization, no cranes, you know. How did they get them to stand up like that? And how did they get these rocks on top? And back when it was first done, every one of the pairs had a rock crossing the top. Okay? I don't know how they did that. I don't know how they possibly could have done that. We would have been hard-pressed to do that without any equipment. Okay? Pretty amazing. Now, this formed a circle. And there's one, there's two, this may be 1, 3, 4. I think there's 12 of these pairs around the circle. Okay? 2 stones with one across the top. I believe there's 12. I don't know for certain. I've never been there. Okay? Some of them have fallen down over the years. Okay? You can see some have trashed. But many of them are still standing. If you placed yourself in the center of that circle and stayed there over long periods of time, you would see that basically something equivalent to, probably not the same thing, as our zodiacal signs, they would have been coming up right perfectly in those positions. Eclipses, equinox is very, and we'll talk about that later, very definitely. The solstices are marked by this almost perfectly. Okay, so not only how did they get the stones there, how did they get them built like this, but how did they get them positioned in perfect order to see all these celestial events? These guys, these ancient civilizations, knew what they were doing. They knew the stars, I think, better than we do. I mean, we may know more chemistry and stuff about them, but guess what? Those guys had a lot of knowledge, an incredible lot of knowledge, and expertise to be able to construct this thing so that each of these things happen in sequence. Perfect sequence. Okay? And they position them perfectly for that. How? I don't know. Okay? Stonehenge. Just one example. There are other rock structures. That's probably the most famous. Okay. Let's talk about what those people actually saw. Okay? Or thought they saw anyway. Let's say they were out there in the pasture taking care of the sheep or whatever, lying on the ground, making up stories about the sky, the stars and the patterns and stuff. And here's what they thought they saw. They thought that the night sky was this huge bowl over them, okay, going down to the horizon, going up ahead, overhead, and that the stars were fixed on them, but they moved around this bowl. So they called this the celestial sphere. Actually, what they would have seen was a hemisphere. It's kind of like if you had a light bulb in the center of the earth, if you can get in the center of the earth, and the rest of it was perfectly clear, and then just the surface of the earth, we were living on glass things, but had the shades there, and the light bulb shined through and projected out onto a bowl. That's what it appeared to be. Okay, that you had these lights out there, these stars and things on this bowl. They call that the celestial sphere. They can only see half of it at a time, so it would be a hemisphere. So all the celestial objects were projected onto an imaginary sphere that surrounded the earth. Okay? Way, 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 way out there. Okay? Now, if you had that light bulb in the middle of the earth, and the earth was clear and all like this, but just had the lines on it, and you had the line that was the equator. Okay, here's the equator right here. It goes exactly around the earth. Now, why is it called equator? Anyone know? Okay, what?
Between,
A little while.
it's like 50-50.
Okay, it's right halfway, okay? If you look at that, what word do you almost see there? Equal, okay? You have these two fixed points that the earth is definitely fixed at, the poles. The earth spins around those poles, okay? The axis goes right through those poles. And the equator is equidistant from each of the poles. Equidistant. Split it actually in two, okay? So, if you had the light in the middle of that globe and everything else is clear except for these lines like this, then the projection of that equator onto that celestial sphere we would call the celestial equator. Okay? Now notice this is tilted. We'll talk about this in a later chapter. So the celestial equator isn't directly overhead. It is tilted somewhat. Okay? The north and south poles align with the Earth's equators and the poles. So the North Pole would be right up there somewhere. The South Pole would be down there. We never see the celestial South Pole because we're here and it's down here. You're not going to see that half of the sphere. You're not going to see it. Okay? Make sense? Okay. So, but we would see the North Pole. We'll always see the North Pole. In fact, I skipped over something I didn't mean to. This one. Anyone know what that is? Almost looks like an artist's rendition of something. It's not. It actually is a photograph. What is that a picture of? I don't know exactly where. I'm going to guess way out in the middle of the desert. Okay? And this is a celestial observatory. Okay? And what it is, okay, and the reason I say a desert, because the desert has very, very low humidity, right? Hardly any clouds at all, right? So, what they did is set up a camera on a clear night, no clouds, and perfectly black out in the middle of nowhere, no lights around anywhere, set up the camera and open the aperture and let it sit there. And what you see here is stars moving around. This is one star moving around for a few hours, but the stars over here moving around for those few hours. And over here, and you see these are actually paths of the stars. Okay? And because they look like they move. And if you go out and look at night, and stay out there long enough, not before this day's class, so do it on the weekend, so you can sleep in the next day, you'll see that the stars actually do move. They move so slowly you don't notice them. But if you go out and look at 10 o'clock at night and then go out again, maybe at midnight or something like that, you'll see they have moved a little ways. Okay? They seem to move. Are they moving? We're spinning. The stars are fixed there. This star here, we're spinning like this, so it looks like it's going. It looks like the star's doing this when we're doing that. Now, I turned the wrong way. It turned like this. So it looks like the star's doing this, we're actually spinning this way. The star's fixed in space. Absolutely fixed. Well, quite good. Yeah.
Or like when we drive, we can feel like it's coming with us.
You what?
It feels like the stars are coming with us.
Oh, it feels like that, yeah. In some senses, yeah. And yeah, for long times, you'll see the stars moving. Part of that is your motion, but more of it is the motion of the Earth making them look like they move. So that's what that's a picture of. So, let's go back to where we were. All right, so that's what we get there. So here is a image of what I was trying to say. You have the Earth somewhere in the center here, and then around that is this celestial sphere, okay? And where the Earth's equator does like this, the celestial equator does like this, just as if you had the bulb in there projecting outward. The south celestial pole, south pole is here, north pole is here, north celestial pole is there, south celestial pole is there. Now we have a star that's very close to our north celestial pole. Do you know what we call it? The North Star. It has one other name I know of. It's Polaris, meaning the pole star. Okay? Now, unfortunately, if you're down in the southern hemisphere, which you can't see, if you look to where the south celestial pole was, there's nothing. There's no star anywhere close to it. It's just blank space out there, unfortunately. So there is no South Pole star. We have the North Pole star, North Star, not the other. And therefore, when we're looking back here, right there is the North Star. Because it never moves. Right now, the North Star is somewhere right there. You just can't see it because of all the light from the sun. But tonight, you'll see it right there. At 10 o'clock, it'll be right there. At 2 o'clock tomorrow morning, right there. It never moves, okay? Because it's right above this, and we spin around, but you see we still see it right in the same location. Okay, all the other stars appear to move around. So, that's where the pulsars are. Oops, went right past it. The north and the south pole stars. Okay. Now, there's that picture again, only much smaller. Let's talk about, we have to have some way to measure things on that celestial sphere. So we sort of make up some stuff. And here's how they work. If I were standing here, and let's say I'm an air traffic controller or somebody like that, and I see a plane over here, how am I going to describe that plane and its motion? Well, I'll say what altitude he has, how far he is above the horizon, and which direction he's going. And that's going to be pretty close to how we say. But we have to say what direction I'm looking. If this is north, maybe I'm looking west-northwest here, and he seems to be so many degrees off the horizon, and he seems to be moving in a northerly direction. So I've given as much information as I can. Well, when you're talking about stars on the celestial sphere, you have to have some way to measure them. So one is going to be the altitude angle. So let's say I'm here, facing north here, and there's a star right there. You see it? There's the star. Well, how far is it? The first is the altitude angle. Above the horizon, go straight up. What angle does that make? So many degrees. Okay? That's the altitude angle. The next is the azimuth angle. What's that? Well, I have to pick some point on the horizon. Okay? And let's say if I'm facing due north here, let's say right here is due east. So let's say from due east, how far around is it there? Well, I can go this way or I can go that way. You determine how far, but the angle from due east around to that right there, that would be the azimuth angle. Okay, you have to define where you're going from. Okay, so those are two things we'll use to determine the location on the celestial sphere. Now, here's another term we'll talk about. Let's face due north, okay? And if you go from due north to directly under the North Star here, and go from the northern horizon, go through the North Star, directly overhead, I'm going to fall backwards, and then go down to due south. What I've just traced here is called my local meridian. My local meridian, my celestial meridian. It's the east-west location of the observer. Okay? So the star was there, my local meridian is here. How far east or west of my local meridian is that star? Okay? So that's what we call our celestial meridian. Objects appear to rotate about the north-south poles. So like I said, that picture right there is showing these stars going in circles. Okay? They left the aperture open probably 4 to 6 hours, and that's why you could trace just a portion of the motion, okay, of the star. But there are plenty of other stars in about the same thing, and they all seem to be going around the North Pole. North Star, sorry, North Pole star. Okay, they appear to rotate around that. If you're in the southern hemisphere, there just wouldn't be a star down there, but all the other stars seem to go around that void space down there. Okay. Now, okay, here we go. The celestial sphere. These are the things we're just talking about. So here's the observer, me, okay? And if I'm facing north here, but I see the star right there, how am I going to describe it? Okay? The altitude angle is from the horizon up to that star, okay? And they say here, 30 degrees altitude. Look at this. I'd say mine is a little more than that, but not too far off, 30 degrees altitude. Oh, they didn't use the eastern, they used south. Due south. So I'm facing the North Star here, due south is here. So how far around from due south is that? How many angles? Well, 90 degrees would get us here, so that would be about 110 or 120 degrees there. Well, the one they showed was from due south to 45 degrees, somewhere right over here. So they're looking at a star at the corner of that light fixture right there. That's the one they're looking at. Okay, but that's called the azimuth angle. Okay, altitude angle from the horizon, azimuth angle from due south. Okay, as you go around 45 degrees east from due south. Sorry, I said that wrong. If this is north and east, they're going this way. Okay, so there's some star over there. I don't see it. Okay. All right. Does that make sense? How you locate that star? Azimuth angle? It's a lot like our latitude lines on the globe. Okay? And azimuth angle, that's altitude angle. Azimuth angle, that's a lot like our longitude lines on the globe. How far east or west from some point? They say due south. On our globe, we do prime meridian. Greenwich England. Okay. We'll talk about that in a later chapter. Okay. Same slide. I don't know what's supposed to go there, but there are some things. Now, every now and then, they'll have these little things, science sketch, and you certainly could do those if you're interested. I'll give you a hint here. We're going to be doing this in the first lab again, but I'll give it to you now. Remember I said the North Star was always right there. Always. Right there. Yeah. From where we are here. Now how did I choose right there? Well, I sort of figured out about what due north was. I think I'm right on that. Does that seem right to you? Something like that. Okay. Let's just imagine this. And then how far up? Well, let's look at our globe here. Let's get on the right continent. And we are about 33 degrees north of the equator. Well, our latitude here is always how high the North Star is there. If you're up in New York City, it's higher because the latitude is higher. If you're closer to the equator, it's closer to the equator. So the distance above our horizon is our latitude here. We're going to do this in lab later, so hang on to that thought. And that's what the science sketch says here at the bottom of page 355. And by the way, in your little thin books, you have 2 page numbers there, I think, right? One page number is the actual number from the original text. The other is the number from that little book. So I'm going to always refer to the original text. All right. There is another one, Concepts Applied on the Night Sky. And let's see if we have that in here. I don't think so. Well, let's see if we do. No, I'm pretty sure we don't. Okay. I'm going to kind of draw this here because this is something useful. When you look up at the stars at night, can you pick anything out of that sky? I mean, I've looked many times. I don't know Perseus from Hercules. They don't just look like a group of stars. I don't see the things. But there are 2 things I see really clearly. The Big Dipper, okay? I can always pick that out. If it's in sight, I can pick out the Big Dipper.
And what if you don't see stars?
What's that? Now, guess what? That's not a constellation. They have a different name for that. The Big Dipper is actually part of a bigger constellation called Ursa Major, which means Big Bear. I've never seen anything that looked close to a bear there. But I can pick out the Big Dipper. Okay. Now, let me point out to you here. I was going to put it on the board. I probably should for people who are not here. So let me try to draw this. I don't draw very well, as you can tell. But let's say the Big Dipper. Let me get my pen set up. And by the way, remember this records everything that's projected on the screen. So when I write on the screen with my ionizing pen, that shows up too. The Big Dipper looks something like this. Let's see. Get the curvature right. Is there one more? Maybe one more. That's the Big Dipper. Something like that. These 2 outer stars on the Big Dipper, on the bail of the big, not the bail, the cup of the Big Dipper, the two outer ones, they're called the Pointer Stars. They were the Pointer Sisters. No, I'm sorry, that was something else. Okay, I'm just kidding. Pointer Stars. And if you look at the direction they're pointing, somewhere over here you'll find another very small. Now the Big Dipper stars are usually pretty clear, large, bright stars. They're going to point to a tiny little star somewhere there. That's the North Star. Now, if you can see it, and I very seldom have been able to pick it out, but it's the end of the handle of the Little Dipper. And I don't probably have this quite right, but its handle does something like this, and its bail is something like this. It's not nearly as clear as the Big Dipper. In fact, most of the time I can't see it. Most of the time I can sort of pick out a little bit of it, but I can't make it all out. Big Dipper I can almost always, if it's a clear night, you can almost always tell it, if it's up. And this is the North Star. And everything else. This dipper goes around that, just like there's a nail there and it goes around it. The Big Dipper goes around it. Everything goes around it. Well, actually, the Little Dipper is not a constellation either. It's part of another constellation called Ursa Minor, the Little Bear. And I've never figured out how they got a bear out of that group of stars. It doesn't look at all like that to me. If you can see it, great. You should win a prize or something. Okay. Now, here's another thing. I can remember reading this in a science book. I'm almost certain I did when I was in school. They thought that even in bright daylight, if you look down into a well, as long as the sun wasn't directly over you, but a very deep well, you could see reflections of the star there. This mistakes and misunderstandings said, no, you can't. Okay, no, there's nothing like that. Also heard that if you had a long enough cardboard tube like you get roll of paper towels on, but really a long one, if you made a long one and looked at it out somewhere away from the sun, you could see stars then. No, you can't. Okay, those were all mistakes and misunderstandings. Okay. That's what that little blurb at the bottom is. Sometimes they're pretty interesting, sometimes they're kind of dorky, whatever. Okay. So let's move on to stars. This is 4.2. We've been talking about stars, and we've mentioned a little bit about them, but what really are stars? Okay, first term here, massive. What does that mean to you? Huge. I mean, and this is talked about with mass. That's how much of the thing is there. Incredibly large. Okay? Now, I'm going to move to the last word here, gas. Now, we usually think of gases as being very light. We don't think of them as being massive. We don't think of them as being dense. We think of them as being very light. We almost think that they have no mass at all, but they really do. But very, very little. But look what it says. Massive, dense, really, really, really dense balls of incandescent gas. What do we mean by incandescent?
I've never even heard that word.
What's that?
I've never heard that word before.
Oh, yeah, you have. Oh, I bet so. What did you used to call the light bulbs?
Light bulb.
Okay, but they were called incandescent light bulbs. They showed forth light. That's what incandescent. Picture this. What word do you almost see there? Candle. It's almost in there, right? Meaning glowing. So great, massive, dense balls of incandescent gas, meaning they're giving off light. That's what a star is. Giving off light, not reflecting light, giving off light. Now, why are they giving off light? Great, big, massive balls of incandescent gas. Why do they give off light? Well, let's start with, we're going to get there in a little bit. So let's just say they're powered by fusion. Now, what does that mean? It's not a type of Ford car. What do we mean by fusion? Okay. Okay. If I say Nagasaki, second. Okay, yeah, now that you're getting at something here, okay? You're getting very close to it, okay? If I were to say Nagasaki and Hiroshima, what would you think?
Explosions.
What kind of explosion?
Yeah.
Atomic.
Yeah, catastrophic, whatever you just said. So what kind of explosion? You may have said atomic explosion, exactly. Nuclear reaction. Okay? Now, both Nagasaki, the bomb that was dropped in Nagasaki and the one that was dropped in Hiroshima, there were two slightly different types of bombs, but they were both fission nuclear reactions. What fission means is splitting. You start with a big, massive, dense atom that is somewhat unstable, which we mean radioactive, and you hit it with something, neutrons, that happen to make it more unstable, and it splits. That's what fission is. And actually, a science teacher I had in grammar school or high school said, think of the word fission, F-I-S-S-I-O-N, that you can split it at the S's. And so that's how I always remember. That's the splitting of big atoms. Okay? Enormous amounts of energy given off by a fission reaction. But that's not what's happening in a star. In the core of a star is a fusion reaction. And that's what Melanie was picturing, was rather than splitting a big atom, you're fusing or forcing together small atoms. Specifically, hydrogen. Hydrogen fuses, and hydrogen is the lightest atom in existence. Very lightest. If you go to the periodic table, which is somewhere in your text, I hope it is, the very first one is hydrogen. Yes?
Can the stars burn out?
What's that?
Can the stars burn out?
Yes, and they do. And we'll get to that later in this chapter. Okay? They're still blowing now, but they're going to burn out by the end of the chapter. Okay. So, all right. So you start with the very lightest atom, hydrogen, fuse it together, fuse two or more of those together, and you produce helium. And you talk about how much energy is given off. Those little bombs over Nagasaki and Hiroshima that destroyed entire cities, single bombs, they're nothing compared to a fusion reaction. It takes multiple fission reactions to make a hydrogen bomb. And they have detonated those before. Those are just incredibly powerful. They ignited a few over some islands way in the middle of the Pacific Ocean in the South Pacific, a long way from anything, almost completely destroyed the entire island. I mean, just massive, massive, massive. So that's what's happening at the core of every star. Fusion reactions are going on there at incredibly high temperatures. That's why the light is given off. I mean, these things are hot. Okay? And what is our sun? It's a star, but it's an average star. Average mass, average heat, average brightness, average size, average anyway. Just an ordinary old star. A C star. You know, it's not a B or an A, it's not a D or an F, it's just right in the middle. Now, we use it as a reference for understanding other stars because it's right in the middle. And other stars are bigger and brighter and stronger and so, other stars are weaker and smaller and colder and stuff like that. So we use that as a reference for other stars. So now let's get back to where these stars began. Okay, now out there in space, in some senses you think of space as being completely empty. Nothing there. There's always something there. Not very much, and it's very far apart, but there are things there. And sometimes they're sort of grouped together. Now, most of the stuff out there is just individual atoms, molecules floating around. They're gases. They're not solids or liquid. There are chunks of things out there, but most of space is nothing, except some stuff out there. And if you have a big enough collection of gas, okay, that's called a nebula. Okay? Now, nebula, if you've heard the term, oh, that's pretty nebulous. Well, that means it doesn't have much shape or anything. That's exactly what a nebula is. It's clouds of gas that are just floating around out there. And they're huge. I mean, just enormous clouds of gas. Mostly hydrogen gas, that's simplest of all the atoms that you have, hydrogen gas. And these gaseous nebulae are just out there. I mean, incredibly large masses. I mean, covering way bigger than our solar system, say, or something like that. I mean, just huge. Okay? Well, something happens. Now, we don't know what it is that happens or why it happens, but somehow a shock wave comes through. Maybe sometime hundreds of billions or trillions of years ago, a star exploded and sent a shock wave through the universe, and it just happens to come together and hit this nebula. And it forces some of those atoms closer together. They were just sort of scattered out there. The cloud, they're there. Forces some of them closer together. Shock waves do that. Have you ever experienced a shock wave? You're hearing one right now. If you hear my voice, that means hold your hand in front of your mouth when you're speaking sometime, and you feel little pulses of air hitting your hand, right? That's what's hitting your eardrum. Tiny little things, and that's why you can hear those little shock waves. Well, this is much bigger than that. It forces the molecules closer together, and what happens when you get atoms and molecules closer together, they start getting attracted to each other. When they're far apart, they don't even notice each other. But when they group together, then they have what they call gravitational collapse. So if that shock wave is big enough and strong enough, and the nebula is big enough and dense enough, then it pushes them together and they start clinging together. Well, when they do, they get more massive. Now they can reach further and pull more atoms in. And then more. And then more. And more. And what's happening, that great big cloud of gas is now collapsing because the atoms are now gravitationally attracting each other. That's called gravitational collapse. Now, as that happens, you have a change of energy. And this is where it really would have helped to have physical science 2 first, right? Because when you have a change of position, that's gravitational potential energy. So that gravitational potential energy, as they get closer together, builds up, and that's released into higher temperatures. Now, this is very similar to take your hands and just gently rub them against each other. Don't feel much to it. Okay? Rub them closer and closer and move faster and faster, and what do you feel? Heat, exactly, because of friction. Okay? Well, that's what's happening here. The gravitational energy is released into higher and higher temperatures because the molecules are banging into each other, creating friction, and higher temperatures and higher pressures. Because now you've got more. What a pressure is force per unit area, or weight per unit per unit volume. That's what a pressure is. That's that per unit area. But on the surface, if you got more weight on it, there's more pressure. Okay? So higher temperatures and higher pressures. Well, this temperature keeps growing and keeps growing more and more of those gases in here. Huge clouds of gases. More and more in. And soon they've become massive, dense balls, okay? More and more, hotter and hotter, and at some point it reaches a temperature that fusion occurs. Those hydrogen atoms now start fusing into helium. Boy, when that happens, huge amounts of energy are given off. I mean, incredible amounts of energy. So before it's been collapsing, getting hotter and hotter and hotter, and greater pressure. But then when it becomes, the fusion starts happening, then it's blowing outward. So now you have a terrible competition going on. It's now entered what they call the protostar, almost a star, okay? The accumulation of gases will ultimately become a star now. Before that, they were a nebulous cloud. And they got closer, but if there wasn't enough of it, they would soon dissipate, okay? But if it reaches that stage, so its fusion does start, now it becomes a protostar, no turning back. That's going to become a star. Not a star yet, but it's going to. That's when you know that will become a star, okay? Now, that star has And this is called stellar modeling here. And by the way, this is just to give you an idea. This is one of those examples that requires you to know stuff from earlier chapters. So we're not going to do it. The Orion Nebula. Now remember I said I could pick out two things in the sky. The Big Dipper is the easiest thing, but that's not a constellation. But there's another one, and it's my favorite constellation because it's the only one I can always pick out when it's up there, is Orion. And Orion is the hunter or the fighter, the soldier, or something like that. And you can tell because it has a star here, a star here, a star here, and has a series of stars, like 5 stars here, and then 3 other little stars here. It's like a belt and a knife or a blade or a sword. And it has some, I mean, you can almost pick out and see, yeah, that does look like a fighter, okay, a swordsman, okay? That's the only one I can pick out, okay, so I like Orion. Well, somewhere in Orion there is a nebula, okay, a cloud of gases, okay? It's about 20 light years across. I said these were big. That's 20 times 6 trillion miles. That's 120 trillion miles across. That's pretty big, okay? That's pretty big, okay? Enclosing a roughly spherical area, roughly spherical, with a volume of about, and then they give this in some incredibly large number of cubic centimeters. Why cubic centimeters? They should have done cubic meters, but still it would be a huge number. Calculate the approximate number of hydrogen atoms in the nebula. If you want to look at that, you can. The math is right. I'll let you look at it. When it comes out to being that the Orion Nebula contains approximately, and they say, about 4.2 times 10 to the 60 atoms of hydrogen, a star like our sun is formed by about 1 times 10 to the 57 hydrogen atoms. That means you could make about 4,200 stars the size of our sun out of that one. Now, it's not all going to become stars, but that's a lot of stars the size of our sun. Okay, so that's sort of fun to look at. Now, since we mentioned that, figure 14.6 on page 357 is a Hubble Space Telescope picture of the Orion Nebula. And they say it's the birthplace of an enormous number of stars ranging in the size from scorchingly hot blue stars, we'll talk about that later, to tiny dim brown dwarfs. Many of the stars are hidden in the dense nest of dust and gas. So that's just one of those pictures from the Hubble Space Telescope. On Blackboard, you'll find 10 more of these. They're just incredibly beautiful pictures. Okay. So what is that star? The stellar means stars, by the way. The models of the stars. Well, all stars have within them a core. Now, if you thought the stars were massive and hot, okay, and dense, that core is incredible. It's absolutely unbelievably hot. The most dense region of that star, because you got all that gravitational pull on it, and that's where your nuclear fusion releases all these gamma rays, X-rays, all that radiation. And guess what, folks? That's all deadly. Gamma rays will kill you within hours, maybe days. X-rays might take weeks, but they will kill you, okay? Those are incredibly high energy rays, okay? Now, even our sun is producing incredible amounts of gamma and X radiation. Why aren't we dead? Well, some of you is a question. Never mind, okay. No. What say?
Ozone layer. Ozone layer.
One more. Ozone layer. Okay, I got what you were saying. Okay. That is definitely part of it. I'm going to extend it a little bit bigger. Our atmosphere. Our atmosphere is our biggest friend. Because our atmosphere, including the ozone layer, blocks all that deadly, or most of that deadly gamma and X-radiation. I'd say almost all of it from entering and coming to Earth's surface. Thank you, atmosphere. If we didn't have this atmosphere, we wouldn't be here. Nothing would be here of life. Thank you, atmosphere. Okay. None other planet in our solar system has exactly this atmosphere that's able to do exactly what ours does. Okay? Thank you, atmosphere. Okay. Now, there are some semi-deadly radiation does get through. We call that ultraviolet radiation. What does it do to you?
It provides the heat and burn your skin or
Okay. If you're saying, meaning sunburn, yes. Okay. What is sunburn? It's killing tissue. It's killing skin cells. Okay. Why do you get a suntan? Your body's trying to fight that. It's trying to send, is it melatonin? Is that it? Or there's some sort of thing, chemical, that it sends, and that's what gives you the tan, trying to fight off that ultraviolet radiation. Now, a few of you are much more gifted with more than others of us, okay? So you don't burn nearly as badly, and you don't get nearly as bad of skin cancers in general. But those fair-skinned, mostly blue-eyed people, freckled, yet red hair, oh, terrible. They have almost none of that to fight, okay? So, that's a different subject. We'll get to that in a later chapter, okay? So that gamma and X radiation that would kill us, fortunately our atmosphere blocks it. Now, I contend that probably, in my mind anyway, the most dangerous job that I can imagine was being, I'm going to give this instance, this really did occur. Many years ago, we decided to put up a space station. It stayed up for a while, but there were some calculations made bad, or something hit it. I don't remember what happened, but after a number of years, it crashed to Earth. Fortunately, it went somewhere in the Indian Ocean or the Pacific Ocean and didn't really do any damage to anybody when it crashed, but it came down. So for a while, the only space station up there was Soyuz, which was the Soviet space station. And it continued operating pretty well for many years. Now, the Soviets they did send people to be on it, but they didn't transport people very well. So they were on there for a long time and various things. But most of the ships that went up to it were cargo ships, unmanned and completely controlled by external things. And so the people on the space station would get their supplies through these cargo ships, and they would sort of guide them in and dock them and then unload them and stuff, and then either eject them or send them back to Earth or whatever they did to them. Well, one cargo ship came up one time and crashed into the space station. I don't know if it was the fault of the receivers on the cargo ship or the senders on the space station, but it crashed into the space station, damaged it incredibly badly, and the cosmonauts that were on board had to retreat to the innermost part, and they were in unbelievably cramped quarters for a long time because it was unsafe to be out. Well, we were also using the space station because ours had come down, so we sent up our shuttle fleet, back when we had a shuttle fleet. We sent them up and sent up crews of men to work on that damaged Soyuz station to get it back into operating order. Now, a cargo ship, great big old cargo ship, crashing into a space station, there had to be jagged metal and, torn up things, ripped. It had to have been an ugly picture. They went up there and repaired that thing. Spacewalks, okay? Guess what? They're outside the atmosphere of the Earth. They have no protection from those deadly gamma and X radiation. And they're out there wearing what? Suits, pressure suits. Now, the pressure, the reason for that is one thing. We'll get to that in a minute. The other thing is, if you've ever seen them, they're silvered. The reason they're silvered is so they can reflect as much of all that stuff as possible. Okay, I still don't know if there's been enough studies done to see if they picked up enough radiation that it's significantly shortened their lives. I wouldn't be surprised if it hasn't, but I don't know that for sure. But those guys out there working in very toxic environments, with that little spacesuit on to protect them, working on jagged metal, if they had gotten one rip of that spacesuit, they're dead. Now let's go back to the pressure thing. They're pressurized. Why? Because here on the surface of the Earth, are you under any pressure right now? Oh, you are? What, school pressure? No, I'm not talking about that. Atmospheric pressure. That same atmosphere that's above us has weight. Do y'all feel it? No, I don't feel it. But you know what that atmospheric pressure is? 14.7. Let's just round it to 15 pounds per square inch. Have y'all ever seen that number before? 14.7 PSI, pounds per square inch. That's a pressure measurement, force per unit area.
That's how you
Now,
build your tires.
Say again?
That's how you build your tires.
That's exactly what you do, okay? Now, a square inch is approximately your two thumbs put together. An inch is about the length of your thumb joints. The two of them together make a square inch. And think about how many square inches there are over your body. Multiply that many square inches by 15. That's how much weight our atmosphere is pushing down on us. Unbelievable. Why is it not crushing us? Because our bodies are pushing out with greater pressure than that. If you get a scratch, blood comes out. It doesn't suck in. So we got more pressure inside than outside. So we're okay. We're balanced. Out there, they're not. If they don't have that pressure of the atmosphere on them, they have all that pressure of their body pushing out. So the pressure suits are pushing against that. If they were to rip that pressure suit, not only would that radiation come in, that wouldn't kill them, because all the bloods and gases, everything else would be spewing out of them into space because of the great pressure inside them, as opposed to the most dangerous job I can imagine was those guys going on their spacewalks, repairing the Soyuz space module. That had to have been incredible. That's way more than what we needed here. Okay, but anyway, if they had lived long enough, the radiation would have killed them in hours. Okay, they wouldn't have lived that long. Now, outside the core is the radiation zone. There's the core. And you talk about hot. I mean, we can't even imagine the temperatures of that. That's incredible. Okay, that's where the fusion is happening. Okay, and it's blowing things outward. Of course, the gravity is pulling them inward, so you have this balance going on there, sort of a ballet going on there. This is the radiation zone. Radiation is being forced outward, from those fusion reactions there. Ooh, that's hot. Okay. And then you get to, that's the radiation diffuses outward. In a single star, it takes millions of years for that to get out. I mean, these are huge. These are huge. Okay? Then you have the outer part, which they call the convection zone. Now you're getting close enough to the surface. The surface is cold out here. This is hot in here. The hot part moves outward, cools off, and then comes back in. That's convection. Did any of your moms or grandmoms ever have that visionware? You remember that pots and pans that were glass? They were sort of amber colored, but you could see through them? You've seen that, okay? My mom used to have some, I don't know whatever happened to it, but you could watch the water boil in that because you could see through it, and it would be in the center right over the hottest part of the eye. Then it would be going up, and it got to the surface, cool down, move down around the edges, and you get that circulation. That's exactly what you get here. The hot air is moving up, it cools as you get near the surface, it comes back down. Because hot air expands, becomes less dense, it moves up. Colder air contracts, moves more dense, and goes down. This is going on here. That's convection going all around the convection zone. The outer part of that, that's what you see as the shell. It's not really a shell, it's hot gas. It's really hot gas. So that's what you see as a star. Okay? The structure from the hot material rising from the interior, cooling and sinking back in. Now the upper reaches are the visible surface of the stars. That's what I was just talking about. The sun's surface temperature, 5,800, approximately 5,800. That's around 6,000 K. Now what in the world is a K? Kelvin. That's a temperature scale. Okay? It's called the absolute temperature scale because 0 on that is as cold as anything, anywhere it could ever go. Okay? So this is 5,000 above that. Now we're right here in this room, about 70 degrees Fahrenheit, which is about 20 degrees Celsius, which is about 293 K. Okay? This is how many times hotter than that. I mean, just incredibly hot. That's the surface temperature. I can't even imagine what the core temperature is. It's probably many more digits on there. K. Never say degrees K. Degrees Fahrenheit, degrees Celsius, K. That doesn't have the degree symbol. Don't know why, but it doesn't. Okay. K. Okay. Now we've moved on to lifetime of the sun. Okay. This is on page 357. It's beginning that last paragraph there and goes on to 358. Okay? Well, this is sort of amazing. Is matter energy, or is energy matter? Or are those two completely separate things? We usually think of them as being different. In reality, they are the same. And you actually know the formula that ties them together. Whether you realize it or not, I know every one of you have seen this formula before. A little known, obscure little physicist named Albert Einstein. I'm making fun. You heard of him? What's his most famous formula? E is equal to mc squared. What in the world does that mean? Guess what m is? Mass. So let's say we have 1 kilogram. That's not much mass. That book may be 1 to 2 kilograms. So it's not a whole lot of mass. Okay? But what are we multiplying it by? Anyone know what c is?
Circumference.
Second, the speed of light that we were just talking about. 186,000 miles per second. But convert that to meters per second. Remember that number that was up here? Incredibly large. Incredibly large. Okay? Because a meter takes thousands of meters to make a mile. So and then square it. It's a huge number, but square it. It gets incredibly large. Multiply that by 1, and that's how much energy is produced in joules. A little bit of mass goes to a lot of energy. That's what happened in Nagasaki. That's what happened in Hiroshima. That's what happens every time you have an atomic or nuclear explosion in your power plants. Tiny amounts of mass are being converted into energy, heat. Okay? Well, talk about tiny amounts of mass. 1.4 times 10 to the 17th kilograms. Okay? That would be, okay, 1, 4, 0, comma, 0, 0, 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 0 kilograms of matter are converted to energy each year. And if that's much, that's a huge amount of matter. Think about how much energy that is. This is our little sun, you know, average star, everything. Bigger stars, much bigger stars, way, way, way more than that. So basically that's talking about 2,700 3-ton SUVs being changed to energy every year. Guess what? The sun's going to burn out one day. Uh-oh. We think our sun was born about 5 billion years ago. Okay, we weren't around to see it, but they've done these calculations. And we think there's enough hydrogen in our sun for about another 5 billion years. So we're about halfway through the sun's lifetime. Okay? Now, the lifetime depends on stellar mass. Which would you think? The more massive stars live longer, or the less massive stars live longer?
Less.
Less. You read it already, huh? Okay. He cheats. Okay. No. Okay. It is. He's absolutely right. Because the hotter stars burn their mass that much faster. Okay. I say burn it. They convert it. They fuse the mass that much faster. So the less massive stars have a longer lifetime, and the more massive stars have a shorter lifetime. So guess where our sun is?
More mass.
Right in the middle. Okay. The less massive stars live for trillions of years. The more massive stars only live for millions of years. Our sun lives for billions of years, 10 billion approximately. So, I won't say living, but yeah, that's how long they're around. Okay. Pretty incredible, huh? Okay. Now, I think I have my watch, but I haven't been keeping up with time. Sorry about this, folks. I get kind of carried away. We started at 1:15. It's now 3:15, 3:20. Let's go a little bit longer, and we'll take a quick break just so people can move around, get blood flowing, and that kind of stuff. Okay. Let's talk about brightness of stars. Okay? This is on page 358 where this begins. There are definitely differences in stellar brightness. You can look up at the stars at night, even in town, and see some are brighter and some are dimmer. Well, what makes for those differences in brightness? One, how much light is being produced by the star? In other words, how hot is that star? So how much light is giving off? Number two, what's the size of the star? Some stars are incredibly tiny, so even though they might be giving off a lot of light for their size, they're not very big. But other stars are huge, I mean really huge, not maybe all that hot, but because they're bright enough to give off light, they appear to be brighter. The big difference, and one of the big ones, is the distance to the star. We are so close to the sun, it looks huge. But to those other stars that may be many times bigger than the sun and brighter than the sun, they just don't seem as much because they're so stinking far away. So this makes up what we call the apparent magnitude of these stars. This was a scheme used to quantify the observed brightness. This has nothing to do with really how hot or anything else, just what it seems like it is. The first magnitude star is about 100 times brighter than the sixth magnitude star. Okay? Now these are the stars. Our sun doesn't fit in these because it's so huge, it just dwarfs them all because it's so close. There are 5 uniform divisions between them, about 20 times each one. Okay, 5 divisions, 20 times each. That gives you 100. Okay? The 6 magnitude stars are barely visible. That's when you're out there in the clear, crisp, unlit area. That dimmest little speck you see out there, that would be a 6 magnitude star. Whereas Sirius is so bright out there, that would be a 1st magnitude star. 100 times brighter than the 6 magnitude star. Okay, now here's kind of the breakdown here. Now, that's going from here to here. That's what we're talking about here. Okay? Actually, maybe, yeah, right here. They say a 0 here, that's what they're calling 1st magnitude, and it goes up to 5, which is the 6th magnitude. Yeah, so, I mean, it's sort of bizarre how they do that. But the sun is up here at minus 25. Now, why they have minuses and plus, I don't know. Okay? So, minus is the brightest. Makes sense to me, right? Okay. The next brightest thing is the full moon, which is not producing any light at all. It's just reflected off the sun, but it's so close, and that's about -12. Okay. The brightest Venus, which is the closest planet that we have to us, that's about a -3, 2.5, 3, something like that. Jupiter, when it's at its brightest, is about -1 or 2. Sirius is the brightest star. Are you serious? Yes, it is. Okay. It's spelled differently. Sirius. And that's the first magnitude star, 0 apparent magnitude. Now, lots of other stars are in between here. The next closest galaxy to us is the Andromeda Galaxy, and that's about +3.5 or 4. Okay? These are getting dimmer as you go. The farthest star that you can be seen with the naked eye, that's around 6. So that's, I guess I said it wrong. That's about the 6 magnitude star. Now, if you use binoculars, you can see them out to a little past 10. Now, Pluto is not a star. It's not even a planet anymore. It's called a dwarf planet. We'll get to that later. When it's at its brightest, it's a +15. So not even with the best set of binoculars you can buy can you ever come close to seeing Pluto at its brightest. Okay, but with a very powerful telescope, they have seen it, of course. And then the naked eye limit with the super large telescope, you can see out to close to +20. Okay, what you can see normally is 0 to 6. Okay. But with binoculars out to here, and with a powerful telescope out to there. Okay. That's the apparent brightness, apparent magnitude. All right. Now they do give an example here. The brightest star in the Earth sky, night sky is Sirius. Has an absolute magnitude of 1.4. Okay. And I think it looks like that's closer to 0 than 1.4, but that must be what they call 1.4. I don't know. Okay. The picture doesn't match what they're saying here. That tells us that Sirius gives off more light than our sun. Because it's so far away, for it to be that bright, it must be. How many times brighter is Sirius than our sun? Well, you have to do an awful lot of calculations there, and you come out about 23 times. Now, you don't need to worry about that too much. So, I'm sorry I even brought that up. Okay, the next term here is something called luminosity, and I don't even remember if they have that. Yeah, there it is. So now we're moving to what we call absolute magnitude. Oh yeah, that was on the previous page. Okay, absolute magnitude. The other was apparent magnitude. This is absolute, meaning actually what you see. The brightness is adjusted to a defined standard distance. So our sun, the apparent magnitude of it was minus 26.7, way up there. Its absolute magnitude is below normal. That's plus 4.8. Okay? Now, what is luminosity? Luminosity is the total energy, and that's why now that I look at it, I misread this. Sirius has a absolute magnitude of plus 1.4. I was looking at the apparent magnitude scale. That's why it wasn't balancing. I said something was wrong here. That's apparent magnitude. Its absolute magnitude is 1.4. But our sun is 1.8, so the ratio of that would tell you how much brighter Sirius is than our sun. And that's how they came up with 23 times. Okay. We won't go there, but that's basically how they did that. So, what is luminosity? Total energy radiated into space per second is directly related to the absolute magnitude, not the apparent, the absolute magnitude. Units correlated to our sun, we call that 1 solar luminosity. Okay? That's not saying a lot, but when you relate it to the sun there. So therefore, Sirius would be about 23 of our sun's solar luminosities, okay, according to that. Okay, sorry. If I ever start flipping slides too fast, stop me, tell me. For any of you who are in class, I think maybe Patel was the only one. Oh, no, yeah, Melanie was too. Goodness, I can't remember her name. Ty. She would let you know if you moved too fast. Wait, I didn't get that. Okay. So don't be shy, be Ty. Let me know. She wouldn't let me get anything over on her. Did I go through any of the previous slides too fast? Do we need to go back? I was just thinking, we were talking about ultraviolet rays causing sunburn. That's one way it destroys tissue. I've experienced a second way, and most people my age and older have too. After a while, just about everybody on the planet is going to get cataracts. If you live long enough, you're probably going to get cataracts. What are cataracts? That's where the radiation from the sun, ultraviolet radiation, damages the cornea, the lens type part of your eye, and it hardens and stiffens and doesn't do what it's supposed to anymore, and you can't see as well. So in my right eye, I've already had one cataract removed. They put in a fixed lens, not a human lens, but it's good for distance, and that's now allowed me to quit wearing glasses. So I can drive now because I can see distance with this eye, and I can read with this eye, and my brain, the body, adjusts for that and uses whichever eye it wants to. Really amazing. The human body is just the most incredible machine ever done. There are some people who can't handle that. They just aren't wired that way, and it just drives them crazy. But
is it similar to LASIK?
No, this is a standard cataract surgery. They just take out the damaged tissue and put in a new lens. LASIK does something else, but yeah, my sister-in-law had that, and she could quit wearing glasses. She had nearsightedness, and it did something about the shape of the eyeball or something, or the lens. I don't remember how it did it, but I've heard it before, but I don't recall. You're going to have it? No. Oh, you're scared to have it? Okay. Yeah. I don't want anything happening that I can avoid. But this eye, I think I'm getting now, so I get so tired reading or looking at the computer for very long. I have a feeling my near vision, that it already had a cataract forming in it, but it wasn't advanced, but that was several years ago. I have a feeling I'm going to have that one replaced too. So, but I don't want to have anything more done than what I absolutely have to. And yeah. All right, everybody got it? Just thought I'd bring that up. Oh, the other thing, especially back in my age of time, there were what we called the sun worshipers. And I wasn't talking about the S-O-N sun either. It was the S-U-N sun. And they would just lay out in the sun for a long hour, get as dark a tan as they possibly could get, you know. You know what they are called now? Prunes. Because that's doing damage to skin, and the more wrinkled basically you see someone is, you can almost figure they were out in the sun more when they were young. The people like, I don't know if y'all remember Dear Abby and those folks, they've avoided the sun like crazy, and in their 70s, their skin was just wonderful, you know. So it damages tissue. Okay. Which, in addition to all that, causes skin cancer, by the way. And I've had one small basal cell removed. This is precancerous here. I put sunblock on it every day. Don't mess around with the sun. Ultraviolet rays still kill tissue. Okay, so now let's look at star temperature. We talked about absolute magnitude, and we did a bit with that. Now we're going to talk about star temperature. The color variations are apparent. Now, of these listed here, which did you say was the hottest and which was the coolest? You tell me. Red is the what? Hottest, and bluish white is the coolest? Exactly backwards. Okay? Red is actually a cool temperature. Okay? Think of this. Okay? You probably have a space heater in your house, or maybe you have a fireplace or something, and when that thing's running, you see it red, and you think, that's hot, right? But you know what's really hot? That flame on your stove. If you have gas cooktop, or if you're down looking at the one in the thing, what color is that flame? Blue. That is hot. That is your hottest.
I've heard that the white flame is the hottest.
And the white flame, the bluish white is even hotter. Yeah, you're absolutely right. I had some argument on which is, if it's more bluish or whitish or whichever. But yeah, that's the hot side. This is the cool side, believe it or not. And here's what you can think of. Really, this is a pretty good way. Does anyone remember what Roy G. Biv stands for?
Red,
Yellow, green, blue, indigo, and violet. Okay? What is that?
colors of the rainbow.
Colors of the rainbow. Red is the lowest energy. Blue, violet is the highest energy. So Roy G. Biv is low to high. The same thing with color there. Color is related to the surface temperature of that star. Now, I think we're going to show some pictures of black body radiation curves. And, let's see if that's a picture. Yeah, here it is. This is, you can do this on any thing that you happen to have out there, any radiation that you have coming in, you can split this up this way. Or you could do an experiment that shows this very same thing. And a guy named Fizu, strange name, actually did this experiment, and it's really a nifty little experiment. Okay? What he did, he had a heater, and it was heating some material. I think it was probably soot, graphite, carbon, that. Heating that at different temperatures, and then he had what was called a collimator. It got it into a very narrow beam, okay, and it would then go and hit on a rotating cylinder. And that rotating cylinder, if it hit anywhere on that cylinder, nothing happened really. But the cylinder had a single slit down the middle of it, on one part of it. And when that came by, the radiation went into it. And the cylinder, as it turned then, the higher speed radiation hit first, and the lower speed hit later. So you had a spectrum that did like this, or like this, or like this, of distributions, okay? The lowest energy, the lowest temperature produced a spectrum down here. the higher temperature here, the highest temperature up here. And this is indeed, when you're looking at these stars that have these different temperatures, surface temperature, remember what sun's surface temperature was? Anyone remember? It was somewhere back here. There it is. Right around 6,000 K, right? So guess where we fit? Where else do we fit? Right in the middle, okay? So here we are, 5,800 would be just a little bit on this side. There we are, that's why our sun is yellow, okay? Middle temperature. We're middle everything, we're average, okay? The hotter stars, whose surface temperature is like 10,000 K, those are the blues, the violets up here. The lower temperature, the red stars, those are around 3,000 K. Half as hot as our sun. These are stars that are on the way out, most of them. Not going to be around that much longer. So, and these are the black body radiation curves, and the Fuzu showed this. You heated that carbon to higher temperatures, you got curves up there, lower temperatures, curves down here. And it did it by distribution of those carbon particles on the inside of that rotating cylinder. We're in between, the sun. The classification scheme and who came up with these letters, I do not know, okay? It's based on temperature, hottest to coldest. The very hottest stars, these may be 10,000 or greater, I think some up to 30,000, are the O stars, and then the B stars, then the A stars, then the F stars, and we are a good old G star, okay? And then the K stars and the M stars. These are the coolest. Not in the cool sense, but temperature-wise, the coolest. Okay. Now, this is the, and this sort of contradicts what you said. I think the bluish are considered hotter. The white would be more in the middle. Okay? 30,000 to 80,000. Now this is surface temperatures. These are blue Christmas, stars. Okay? The spectrum, everything in them. Ionized gases, mostly helium and hydrogen. Little else. Short-lived, very rare stars. If you see one, watch quickly because it's not going to be there long. Okay, maybe only a few thousand years or so. Okay, so very short-lived, incredibly hot on the surface. Okay, the B stars, the blue stars, these are again bluish, maybe not quite as brilliant blue. 10,000 to 30,000 K surface temperature. The spectrum are neutral helium, none of it ionized. Do y'all know the difference in neutral, meaning balanced atoms, and ions? Do you know that difference? Okay, let me go to that real briefly with you. Let's take, they're called the 4 phases of matter. Back when I was in school, they were called states of matter, and then we called them 3 states of matter. Now they're called phases because now the quantum mechanics is here, state has a different meaning. So, 4 phases of matter. The first of these is a solid. Okay? A solid has a fixed crystalline structure. Every atom's in its place. All the atoms are about the same distance apart. You know, they have a fixed shape, fixed volume, fixed everything. Now, you can heat them. They'll expand a little bit and contract a little when you cool, but it's very, very small. Very small. What happens if you add energy to a solid? Most solids, what does it become? A liquid. You melt it. Now those atoms don't stay in the same proximity, the same place, fixed position in a crystal structure. Now they're free to move about each other. So now you don't have a fixed shape, but you have a fixed volume. That liquid is going to take up the same volume. And sure, if you heat it, it'll expand a little bit, cool it, it'll contract a little bit, but by and large, it doesn't change much. Okay? What happens if you add more energy to it? It becomes a gas. Now you lose that proximity. They don't even stay around each other. They just float anywhere they want to. So no fixed volume, no fixed shape at all. What happens if you add more energy to it? You become a plasma, exactly. What is a plasma? No longer neutral atoms, but you've either knocked off electrons, making a negative ion, or you picked up an electron, making a positive ion. So now it's ionized. That's what it means to be ionized. Is you've got at such high temperatures that it's no longer neutral, it's now either gained or lost electrons. Do we have any plasma in the room? I see solids, see a little bit of where liquids were anyway. There's plenty of gas in the room. Is there any plasma? Where? Okay, in our fluorescent tubes here. That's what's giving off the light there. That's why they don't get nearly as hot as your incandescent bulbs. It's gone already, but there's that word, incandescent bulb. You call them light bulbs. Okay, incandescent bulbs, because that's done on heat. You're heating a filament, and that's giving off light. It's glowing. In the fluorescent tubes, they don't get nearly as hot. That's why they last longer. They don't use as much electricity to keep them lighting. But what you have there is ions flying back and forth between. In there, it's called a ballast. Very high, very powerful capacitor, builds up a huge potential difference, and the ionized gas goes between the two. And as it passes, if you've ever seen a broken fluorescent tube, you see that white powder that's on the inside? That's a phosphorescent material, meaning that when energy goes by, it jumps up an energy level, the state does, and then when the energy passes, it drops back down. That gives off a photon of light. Different mechanism for heating something up till it glows. That's raising and lowering energy levels. That's what's happening there, because they're ionized. So in this one, they're neutral helium, none of it ionized. Okay? Then you have the A stars, which are still bluish in color, but getting more bluish-whitish, 7,500 to 10,000 K. The spectrum with no helium, but it's strongest in hydrogen, some magnesium, calcium, a little bit heavier elements in it. Then you have the F stars, which are the white stars. These are 6,000 to 7,500 K. Spectrum is ionized calcium and magnesium, so it's sort of going backwards, it seems like. Neutral atoms of iron, which is interesting, because iron turns out being the most prevalent atom in the universe, is in some senses, especially in solids, so I'll put it that way, okay? We'll get to that later, okay? Then we get the good old G in the middle with yellow, and that's where we live. 5,000 to 6,000, we're 5,800, remember, K on our surface temperature of our sun, not us. The spectral type of the sun, the spectrum shows 67 elements in the sun. Guess how many elements we have here on Earth? Naturally occurring. Maybe a few more than 67, but right around 67. The others are so rare we hardly see them. So that we came from the same place as the sun. Okay, and then the orange-red, those are 3,500 to 5,000 K. Spectrum packed with lines of neutral metals. Okay, so many metals. And then the M, the coolest, the reddish stars, 2,000 to 3,500 K. The band spectrum now, not just atoms, molecules, titanium dioxide, other spectral types based on molecules present in the spectrum. Okay, so those are the star temperatures. Seems like we're just randomly going after things. We talked about absolute magnitude, now we're talking star temperature. Why? They're not relating these too much. Why are we talking about these? Here's why. This is how we classify stars. Okay? A couple of guys. Hertzsprung, seems like he was from Austria or somewhere. Let me see if I can find that so I can say it for sure. Denmark. Egnar, or something like that. Egnar Hertzsprung of Denmark and Henry Russell of the United States independently developed this scheme of a diagram, and they put the temperature Surface temperature of stars here, that's where we're talking about them, from 3,000 or below 3,000 up to 40,000 or so. We didn't see many that were that high. Very incredibly hot there. The absolute magnitude here, okay, and this is on the scale. Remember, our sun is about 4.6 or 4.8, somewhere right around in there. The brightest star that we see is Sirius A. Is here about 1 point, whatever it was, 7 or something like that. Okay, there are hotter and brighter stars out there, but Sirius is close enough so we see it as the brightest star. Okay, so anyway, they plotted the stars this way by their temperature on one scale, absolute magnitude on the other scale, and they found they grouped like crazy. And when they grouped, they noticed special things about those groups. These are what we call the main sequence star. I consider this the purple eel in the middle, okay? These are stars in the middle of their lifetimes, regular stars doing their things, okay? Now, when the stars begin to go near the end of their lifetime, one of the things they become is much bigger. These are called the giants, okay? These were stars that were main sequence here, tend to be fairly large stars here. They become the giants, and these are huge stars. The trouble is they get cooler on average, but they're brighter on average. Then you have the supergiants, which are the incredibly massive stars that are both very, very high magnitude with a whole range of temperatures, okay? Okay? Now, later, even these will then collapse on themselves and become much smaller stars. Some of them are still pretty hot, but many of them cooler, and certainly their absolute magnitude is much, much less. This is toward the bottom of the scale, and these are called the white dwarfs. White meaning they're still pretty hot. Okay, remember white was pretty hot, but they're much smaller. The supergiants, some of these are red, okay, but they're so big they're much easier to see. All right. So each dot here represents a star. Now this isn't all the stars. That's certainly not billions of stars. These are just representative stars, and they're all the ones that are in there. They are normal stars, then the giants, supergiants, white dwarfs, and they all sort of cluster together like this. Supergiants, that's not as tight a cluster as the others. The white dwarfs, maybe not quite as tight as the others. Okay. So the main characteristic grouping, the main sequence stars, these are the stars in the middle part of their lifetime, just carrying on doing what they normally do. Then you have the red giants, which are here, and the supergiants they're calling the novas. Those are really huge and hot and thing. And then the white dwarfs down here. Now, what I've never figured out about this slide is why they put this in here, okay? The Cephid, I guess is how you call that, Cephide, I don't know, variable stars. They have a little paragraph on this, and I'll basically just about read it to you. Stars such as the sun emit a steady light because of the force of gravitational contraction balanced by the outward flow of energy. Now, I thought for sure, let me just go back a little bit. Maybe it's still coming up. I guess it's coming up. There's some things about this chapter I don't understand why they put it together this way, but okay. Here's what it said. Most stars, or a lot of stars like the sun, everything's sort of normal, average, okay? Steady stream of light, okay? However, there's some stars that are called variable stars. They're stars that change in brightness over a period of time. In other words, they get brighter and then dimmer, brighter and then dimmer. Now, this may be a very long period of time, or it may be a very short period of time. A Cepheid or Cepheid variable is a slowly changing variable star that is used to measure distances. Okay? There is a general relationship between the period and the brightness. The longer the time needed for one pulse, the greater the overall energy output of that star. The period brightness relationship to distance, calibrated by comparing the apparent brightness with the absolute magnitude, true brightness, of a Cepheid variable at a known distance with a known period. Blah, 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 huh? Using the period to predict how bright the star would appear at various distances allowed astronomers to calculate the distance to a Cepheid given its very apparent brightness. Now, to me, I can read that paragraph over and over and over, and the individual words make some sense, and some of the sentences do, but I still don't get the whole picture of it. I think they try to grossly simplify it. But the guy who came up with this, you've heard his name before, you're going to hear it repeatedly. Hubble. Might be a good paper topic, folks. He came up with this method of estimating distances using these variable stars, the Cepheid variable stars. Hubble also came up with the concept of the universe expanding at an increasing rate, and it's called the redshift. Okay? Things are going toward, because things are getting further from you, the wavelengths seem to be increasing because they're moving away from you, moving toward the red. Longer wavelength, lower energy. Okay? You'll see Hubble's Space Telescope was named after him. There's Hubble's Law. There's Hubble everywhere. Okay? So, quite an interesting character. And any of those things about Hubble you could write on too. All right. Let's now move to the life of a star. This is where it's coming. Okay. Again, it seems like this should have been back earlier, but here it is now. What I was looking for. Remember back, several slides ago, we said that masses of gases, okay, the nebula cloud, when it starts collapsing because of that pulse or whatever forced the molecules together, now they're collapsing. When it got hot enough, it became a protostar. So that's where we're going back to, that protostar stage. What we've had is gravitational collapse as those molecules are getting closer and closer and closer together, as they do in atoms and molecules, getting closer together. And as they do, the density increases, the temperature increases, the pressure increases. So everything's getting hotter and denser and more higher and higher pressure. And finally, at about 10 million K, okay, this is core temperature. This is not at the surface. 10 million K fusion ignition temperature. They say ignition as if it's burning. They use that term, in fact, but it isn't. It's fusing, okay? And that's when fusion starts. So now, and this is what I was trying to describe before, you got gravitational collapse pulling things together, but now you have fusion pushing them apart. That creates what they call the dynamical equilibrium. Dynamic meaning changing. Everything is changing, constantly changing, but it's trying to reach an equilibrium. And you can almost imagine these variable stars may be more dynamic than the others are, and that's why they're variable. I don't know, okay? But now we have the inward force of gravity, outward pressure of the fusion energy. They reach some sort of equilibrium, and the star becomes, the protostar becomes a star. When finally that sort of equilibrates, and now it's sort of resting happy, fusing like crazy in the core, radiating, doing all the other stuff, finally it's main sequence star. Okay? Before that, it didn't show up on the star charts at all. Okay? Now it's a main sequence star. Now it may be there for millions of years if it's a huge star, very hot star, billions of years if it's an average star, or trillions of years if it's a small, less than ordinary star. Okay? And here is another diagram that we saw before. We see the core. That's where fusions happen, pushing pressure outward. This would be the radiation zone type stuff in here. but then you have all that mass is still pulling stuff inward, and that's what keeps it from blowing apart. And that dynamical equilibrium between the inward force due to gravity, the outward pressure because of the fusion, that's what keeps the star a star. It keeps it at whatever size it happens to be. Okay? Our sun sitting along like that, dynamically at equilibrium. Okay? Now, I went right past 3:45. Do y'all need a break? You do? Okay, let's try to, and maybe y'all didn't know this. I'm required to call roll twice. Once for the class part and once for the lab part. And since we're, quote, in the lab part now, because it's past 3:45, 15 minutes past that, Zaria is still here. Rod is still here. Okay, I'm sorry, I couldn't remember which one were you. Bertram didn't make it in today. I don't think he made it in last time either. Samaya is still here. Corey is still here. Okay. Thomas Earl is still here. Seth. Did we lose Seth? Was that Seth? I don't remember. Okay, we lost Seth, it looks like. No, wait. Seth never was here today. Okay. So let me... Got Bertram, yeah. Seth didn't make it in today. Okay? Brandis, Janelle, Lane, as far as I know, didn't make it in today. Rashad? Rashad, did we lose Rashad?
Yes.
Yeah, okay. So he's gone. Michaela is still here. Yeah, I thought I was being clever. Cole. Yeah, okay. I circled letters in your name and then couldn't read it. Okay. Patel still here. Reggie still here. Diego. Yeah, still here. Radeja? No. Is that right? Okay, Radeja. Okay. Still here. Melanie is still here. Derek didn't make it in today, did he? I don't know Derek, so. And Marcus. Did we lose Marcus? Was that Marcus? Looks like we lost Marcus. Okay, let's take a quick break. See if you can keep it less than 5 minutes. Okay, and I'm going to turn off the projector right now so it's able to bub a little bit, and we'll come back and wrap up. Okay? Get up, stretch, move around, get blood flowing. Use the restroom. Watch where you pay. Okay. Oh, I meant to turn off the recording. Otherwise, we'd be recording a lot of dead time. So let me pause this. And I turned on that already. Okay. So I think we hit this one pretty well. Any questions on this slide? Did everybody get it? Anyone still writing on it? Okay. Some, okay. I'd have left it on during the break if I had known some of you were still writing. Sorry. Okay. So at this point, we've entered the purple eel, okay? That string of main sequence stars, okay? Now, what happens then? Well, as we said, as I sort of waved my arms about before, they start in here, but after a while, they start using up all their fuel. In other words, all the hydrogen is fused to helium, okay? And then here's what happens. They enter what they call the red giant stage. The hydrogen in the core is used up. Basically exhausted. All the hydrogen has been fused into helium. The core collapses because remember, it's in the fusion pushing things outward. Okay? Now it collapses. It heats up big time, really high. Okay? Now, when the core heats, it blows the outer shell outward. Okay? The outer shell is being blown outward because of the heat from the inner core being collapsing, because there's no more fusion. Well, when the outer shell expands like that, it cools. And when it cools, it goes down from being blue or white or yellow or orange to red. And that is what we call the red giants. Those are those over in here of the Hertzsprung-Russell diagram we call the giants. Okay. Now, here's what we talked about before. I've already mentioned these. The O stars, remember the hottest stars? They only live millions of years, which seems like a long time to me, but okay. Remember we said the Earth, around 10 billion, we were the G stars, the middle, sorry. What hit me there? And then the M stars, those really cool little bitty stars, they go for trillions of years before they use up all their hydrogen. Even though they burn much cooler, that means they're not burning as fast. So they didn't have as much, but that takes them a lot longer to use it. The mass determines the ultimate fate of the star, which is what's coming up next. The mass determines how long they live, but it also determines what the ultimate fate is. And that's what the next slide is going to illustrate. Okay, well, I'll wait for a minute until you get that. Well, I think this is going to stay there. Let me see. Yes, here it is. So you started in the main sequence here, okay? And then when the hydrogen was exhausted, the core collapsed, the outer shell expands, cools, it becomes a red giant. And that was in this phrase, part of the Hertzsprung-Russell diagram. Okay? Now, some stars move on up here. And this was the supergiants. Okay? So let's see. Here's the cooler stars down here, the hotter stars here, the brighter stars up here, the dimmer stars down here. Absolute magnitude. Okay? This is just showing how you're moving through the Hertzsprung-Russell diagram without the snakes and things in there. Okay. Now, you'll have to kind of keep this in mind because the next thing they're going to talk about, let's see if it, oops. Did everybody finish this slide? No, not quite. Okay. Okay. Everybody got it now? Okay. Hope you take it as a picture, not mine. Okay. Now. So now that's moved up here. So here is the end stage. Okay? Let's start with, okay, we're in the red giant stage. Whatever star we have, we got there. So late in that, the further core is collapsing and heating hotter and hotter and hotter as it collapses. Now the bigger cores, they're going to collapse and get hotter and hotter and hotter. Smaller cores, maybe not as hot. But what happens if it continues heating as that collapses, just like what happened back in the protostar state, if it gets hot enough, now this requires way more heat than what we had before, we actually get helium fusing to carbon. Hydrogen fused to helium, then the helium fuses to carbon, okay? And when that happens, your radius and your luminosity decrease, okay? Now, and it moves back in toward the main sequence because now it's operating again, okay? Because, now, there's part of this that sort of seems like it doesn't make sense, but it kind of does. You would think when the fusion started again, it would be more outward pressure, but the deal is here, it's not continuing to heat. It reaches an equilibrium, and that's why the radius decreases again. The luminosity also decreases because it's not quite as big, but it moves back to a main sequence. So it comes back in the main sequence somewhere here. Now it's not doing hydrogen fusing to helium. Helium's fusing to carbon, which is a hotter process. Okay. Now, that happens. Now let's go to the less massive stars. The helium, you didn't have that much to begin with. I mean, some, but now the fuel is being used up. So now the helium and the hydrogen fusion in the shells are exhausted. There's nothing else to do. The instabilities blow off the outer layers, okay? I mean, just erupt and blow off those outer layers, and that forms what they call a planetary nebula, okay? Now, I know y'all are probably writing, but hold on this for just a minute. I want to go way back. Right there. The very first picture we saw at the beginning of the chapter, I was thinking about talking about it then, but I decided not to quite yet because we didn't know what we're talking about then. This is a nebula, which is a cloud of gases that's been blown off in the star. I'm guessing that's what remains of the core. Okay? Okay? That little bit here. The outer gases, the radiation zone, whatever that next part was, the convection zone, all that has been blown off. That's what's happening here, and you're left with a tiny little core. Still really hot, okay? Very hot, but that's in the middle. This is what we call a planetary nebula. Has nothing to do with planets, except planets go around the thing. This is going around the center, the core. Okay. Let's go back so you can pick up writing again. Getting close. All right, here we are. So the instabilities blow off the outer layers into a planetary nebula. The outer part is blown off into a cloud. This is where those clouds of gases came from. They used to be stars, okay? How many times has it gone through this cycle? We don't know. The carbon core, remember the helium fused to carbon, so what's left is carbon. It contracts because of gravitational collapse again, and that produces enormous amounts of heat, so it goes to being a white dwarf. Dwarf because it's contracted, white because it's so hot. Okay? But guess what? Over time, which may take years, decades, centuries, millennia, whatever, takes a long time, but there's no new fusion going on. It's hot because it was left over, gravitational collapse, but after a while it cools. So now we have a black lump of carbon. Okay? Now when they say black, do they mean color black? Maybe. Maybe not. But it means it's no longer emitting light. It was emitting white before because it was so hot. Just like an incandescent bulb, it's so hot it's emitting light. But there's no fusion behind that. So after a while that cools off and it's no longer emitting light. Now, the very first, this is what, we used to have a physics instructor here. He's part-time, but he's a real neat guy named Leonid or something like that, but we call him Leo Bolshinsky. Good Irish name, right? No. He was from Russia, actually. He was from Ukraine. He was Russian by lineage. But when Russia, the biggest of the Soviet states, gathered all the others into the Soviet Union, they sent out Russians to live in all these other Soviet states because they wanted to make them more Russian. They didn't want them to maintain their cultural identity. So his family many years back had been sent to Ukraine, but he worked for the Russian space agency, the Soviet space agency. Okay? But he lived in Ukraine. And he was considered Ukrainian, though he was naturally natively Russian. Okay? But then when the Soviet Union fell apart, they were no longer able to keep the countries together, okay, those states together, But they didn't let the Russians move back to Russia. No, they said, no, you've been in the Ukraine long enough, you're Ukrainian. Well, Russia still kept a space agency. Ukraine couldn't. It didn't have enough money. It wasn't big enough. It wasn't powerful enough. It wasn't rich enough. So Dr. Bolshinsky was left in Ukraine with not much he could do, okay? They didn't have a good space agency. They were a poor country. So he immigrated to the U.S. He was a real neat guy, and he knew a lot. He could take anything and make it work. He was just so good, and he worked here for us some. But then he got a job offer up at Huntsville, so he was teaching physics and astronomy at UAH, but working for NASA. Exactly what he was trained to do. So, anyway, he told me the story of the first white dwarf that was discovered. You know, they're really small. Even though they're pretty intense white, they're very small. So it took a long time before they found them. Okay? And when they did, they went through all this and figured out what had happened. Okay? And that's how they became that white dwarf. Okay? Now, physicists, you understand, are rather strange people, right? They're just rather strange. And that first white dwarf, when they figured out it was carbon that had been fused together, you might say, under high temperatures and pressure, really high temperatures and pressure. What happens to carbon under real high temperatures and pressure? You want to know? Girl's best friend? Diamond! They make diamonds. So the physicists said, hey, carbon at that kind of temperatures, that kind of pressures, there had to be some diamond in there. So guess what they named that first white dwarf? Anybody? Lucy. Why not? Are y'all old enough to remember the Beatles? Do you remember Lucy in the sky with diamonds? They named that first white dwarf Lucy after a Beatles song. Physicists are strange. Really strange beings. Okay. I'm one. Okay. So, cools to a black lump of carbon. That's why I don't say it's just colored black. It may be filled with diamond. Who knows? Okay? That may be where the diamonds that we find in the earth came from. Something very similar to that. At one time, that was part of a white dwarf. Who knows? Okay, so that's the least massive star. And by the way, here's a better picture of a planetary nebula. Okay, this isn't in color like the other was, but it shows that the nebula, the cloud of gases around here, and there's that white dwarf in the middle. The core that was left, compressed, hot, white, but not producing any fusion, and the masses of gases being blown out into space. And they're expanding. It seems like a slow rate, but when you realize how big that is, it's going pretty fast. Okay. So that's the less massive stars. They wound up being white dwarfs, which later cool to become black lumps of carbon. That becomes what we call dark matter. You'll see that later. Okay? Now, the more massive stars. What happens here? The more mass, the more gravitational contraction, the more heating you have. Now what happens is that carbon that's in the center, that was the end state for the less massive star, it still is contracting and heating. Now the critical temperature is 600 million K, and at that point, the more massive stars actually get carbon fusion. And now these heavier nuclei fuse, and they fuse up to iron. After iron, they don't fuse anymore. There's something about the thermodynamics of the process. That's why iron is one of the most prevalent elements in the universe. It's made up of, makes up the core of most of our planets and many other things. Iron is just out there. Okay. Now when that happens, all the fusion energy sources are used up. It's not going to fuse any past iron, not in normal fusion that we would think of. now the energy of the expansion pressure is lost. That came from the fusion. And now this dynamic equilibrium is disruptive. It collapses on itself. I mean, it collapses big time. And that's what forms the supernovas. So the red giants were here, and they moved back to the main sequence. Then the supergiants were up here. Those are the supernovas. And they collapse again. Okay? And this time when they collapse so rapidly, so energetically, so incredibly, with so much force, they actually form elements beyond iron. Because this process is not normal fusion. That is the nuclear reaction. This is actually forcing those elements into bigger and bigger molecule atoms. And that's where your elements beyond iron. Iron on the periodic table, just not that far down there. It's number 26 out of 100 and some. Okay? If normal fusion doesn't take you any further than iron, how do we get these other things? It's from these supernovas when they collapse and rebound again and form these heavier elements. But at much, much lower quantities. And when that happens, these elements beyond iron are created in that explosion, distributed throughout the universe, and that's why we have traces of all those where we find them.
So do we still see some
What's
of the
that?
stars? Do we still see like remains of some of the stars that died?
Actually, we probably are remains of some of the stars that died. Because when the sun formed it gathered things from all around it, and it's probably remnants of those stars that died. Yeah. So we may be parts of those dead stars, some of our substance. Okay. So the subsequent events depends on the mass of the remaining core. Okay. We got the supernovas happen, blowing things up. What happens to the remaining core, though? Remember, the remaining core in the smaller stars, that became a white dwarf, and then a black lump of carbon, okay, in whatever form. Well, what happens now depends on how big we are. Now, the remaining core, now this is just a core. It's blown most of the star out into space, okay? But the remaining core, believe it or not, just that little bit of core that's left, is now about 1.5 to 3 times our whole sun's. So these are really massive stars. They've blown out so much into space, still the core is 1.4 to 3 times our solar mass, our entire solar mass. Okay? Here, the gravitational pressure here is fusing, and guess what? Remember the parts of an atom? You have protons, which are positively charged, neutrons, which are no charge, neutrally charged. The neutrons are just slightly bigger than protons. Not much, but just slightly, but almost the same. Almost identical, except they have no charge that has positive charge. And then these tiny, tiny, tiny little electrons that have a whole negative charge. But they're almost massless, just have a tiny amount of mass. Well, what happens? The gravitational pressure here fuses the protons and electrons together so that they all become neutrons. That's what a neutron is. It's a fused proton and electron wiping out the charge but making a little bit more mass than the proton has. Okay? Now, that's why we call them neutron stars. These are the more massive stars, but not the most massive stars. Now, a neutron star that is rotating is developing a magnetized. Okay, start over. There are some of the neutron stars are called pulsars, which means pulsed star. Pulsar. It's a rotating magnetized. Now, I can't quite tell you exactly why they're magnetized. Usually, magnetic fields are produced from the movement of charge. But if you've combined all the charges in the neutrons, where is the charge? There must be some residual charge there, and that becomes highly magnetized. And when this rotating, highly magnetized neutron star is doing this, that moving, changing magnetic field, because it doesn't just spin like this, it precesses when it spins. So now you have a changing magnetic field that produces a signal. And those have been detected from way, way, way far away. In fact, the little blurb at the end of your chapter, every chapter has a science person mentioned. And the woman mentioned at the end of this chapter, I think her last name was Burrell. She was the first astronomer ever to detect, identify a pulsar. Pretty momentous time in the field of astronomy. And guess what recognition she got from it? Almost none. Why? She was working on her PhD, but wasn't a PhD. Her bosses, who didn't discover it, but she was working under them, because it was discovered under their tutelage, they got the Nobel Prize. She didn't. She was not even named in it. Multiple ones of them were named, but they had to have the PhDs. She was not. Now, a little bit of that maybe was the archaic rules they had, but the other part was the insidious sexism. That's the only way I could think of it, that she did not get the recognition. Now, her bosses screamed bloody murder. They said, no, she should be named in this award as well as us. She's the one that discovered them. The Nobel Committee said no. I think they shared the prize with her, but she was not recognized for it. So I think they were decent people, but... Okay. Now, that's the big, big, big stars, but not the biggest stars. Okay? Biggest stars, this is what happens. The remaining core now is greater than 3 solar masses. Goodness gracious. Our whole sun, more than 3 times that, is still in the core after everything else is blown up. Well, what's happening now? Gravitational collapse overwhelms all known forces. We don't understand what's happening here. Not even light can escape from this. You get pulses out of the neutron stars. Here, everything's getting sucked in. Matter's getting sucked in, light's getting sucked in, energy's getting sucked in. We don't know what's happening there. And this is what we call a black hole, because no light comes out of it at all, okay? So it's incredibly dense, compact object, and frankly, I don't think we'll ever know what's in a black hole. Maybe somewhere way in the distant future we'll figure it out. But you see, you can't study it. You can't get close enough to measure it because nothing's there to measure, because everything's getting sucked in. Nothing that we can detect is coming out. Now, I say that, and now they have determined that sometimes they will have flares come out of them. And maybe if they can study those closely enough, and intensely enough, they might figure something out. Right now, it's a mystery. It is a total mystery. Okay. So here is a diagram, and your book has one that I think neater to look at than this one. Yours is on page 363. Okay. It's just a bit more dynamic looking than this is. It's got more color, and it's not so straight line, it's curved and all. Way, way back when, it started as this incredibly large mass of gases. Okay? Gases, though, not anything connected. Something comes along, some pulse comes along, forces some of these closer together, they start gravitational collapse. As it gravitational collapse, it heats up. As it continues, it heats up, pulls in more of the mass. More of the mass gets hotter, 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 more mass, more hotter. And finally, it gets so hot, you have fusion. And when fusion is just beginning to start, you have what you call a protostar. At that point, it's going to become a star. Back here, it could have just been a pulse set of gases. They sort of went together, they drifted apart, nothing happened. Once that gets hot enough to have fusion, and it does begin, it's going to become a star, so that's called a protostar. And there may be a long period there, I don't know how long, but anyway, till it settles out and forms a main sequence star. That's the purple snake, okay, or eel or whatever. It lives there for whatever its lifetime is. Millions of years if it's huge, billions of years if it's average, trillions of years if it's small, but it's a main sequence star and stays there for a long period of time. So let's start with those low mass stars. This would be the very low, and we might even be in the big mass, mid mass, not big mass. So anyway, when the low mass stars, what happens here, the main sequence star is fusing hydrogen into helium. So you're losing hydrogen, gaining helium, and at some point you use it up. Okay? And when you use it up, either low mass or high mass, or really the mid mass or the high mass, what happens then, the core collapses because there's no more fusion, but it gets so hot that it blows out the outer part, and that becomes a red giant. Because as it expands outward, it cools and goes from being whatever color it was, orangey yellow here, yellow white here, blue there. Okay, whatever color it was, it goes to being red. Okay, red giant. Okay, now the low density stars, low mass stars, it basically collapses and becomes a white dwarf, and then a cold lump of carbon. Okay, with or without diamond, you don't know. The mid-mass star, probably closer to where we are, at first is going to be a red giant. Okay, again, same reason as before, red giant. But then when it collapses again, and you get helium fusing to carbon, and they did leave this out. This sometimes happens that helium fuses to carbon, and then it goes back in the main sequence for a while as a helium fusion star, and then comes back into this. But at some point there, after it's used all that up, the core collapses again and blows off the gases into a planetary nebula. What's left over in here becomes a white dwarf, and it follows the same pattern here. So one of these or something in between is what's going to happen to our sun. How long will B be around? Probably by the time the sun becomes a red giant, it's already grown big enough that it's going to engulf the Earth. Mercury, certainly, Venus probably, Earth probably, maybe get out to being big enough to even suck in Mars. Who knows? We won't be here. No one will be there to talk about. All right, then the high mass stars. They become red giants that are massive red giants, okay? And then they collapse, and start carbon fusing to iron. And when that happens, and they've used all that up, then the explosion is really massive, much bigger than a planetary nebula, a supernova, and the core could become a neutron star if it's 1.4 to 3 Earth masses, or if it's bigger than that, bigger than 3, it actually becomes a black hole, and nobody knows what's happening there. It's sucking in energy, mass, and everything from everywhere else. You have no way of detecting, except if you're studying that portion of space and suddenly you get no signal anywhere, and a star you were following here, suddenly you don't see it, and then you see it again, it went behind the black hole because no light came through. Okay, so that's your summary. The one in your book is a lot nicer. It's just really a neat little picture there. I wish it were on this. And why they do this, I don't know. Here they have low mass, here they have mid mass, here they have high mass. This is the lower high mass, and this is the higher high mass. Seems like to me these two should be flipped. Because the black hole would be the highest mass, and the neutron star in between. They do it that way. They did it in your book the same way, and it just doesn't make sense to me that way. But it's still true. They just didn't follow the same pattern. Okay. Now, by the way, in your text on page 363, there's another incredibly beautiful picture taken by the Hubble Space Telescope. I think this one may be in one of those 10 that I put out there. It's a blown-off outer layers of stars, ring-like structures in the Cat-Eye Nebula. I believe that's in here. Planetary nebula, actually the edge of a bubble of dust, blah, blah, blah. I'll let you read that. Okay. And then on page 364 is a picture of one of those neutron stars, and you see a little bit like the Earth, not nearly, I mean, we're over close, but here is our axis of rotation, right? Here is the north magnetic pole, right there. Not quite where our axis of rotation is. The south magnetic pole is down here, but I can't find it now. Goodness gracious, where is it? It's near Australia. There it is, right there. So it's way off from the South Pole. So if we had a strong enough magnetic field, when we're spinning like this, and yet our magnetic pole is going like this, and if we were strong enough, someone studying this from far away would see a little bit of a pulse every time that magnetic pole came around the axis, okay? That's what your neutron stars do in spades. I mean, big, big time, because that's much, much more powerful than what we are. Okay. Now, there's a closer look here, observing with new technology. They talk about all the different things they use: X-rays, infrared, gamma rays, boy, all the radio telescopes, all the things they use to measure all the things they see out in space, and they put the composites together. What I was talking about before, Science and Society on light pollution, there's a good blurb there with a few questions. That could be a paper topic. In fact, any of these things could be a paper topic. All right. Okay. Now, and that figure 1415 on page 365 is a jet of particles streaming out of the center of the galaxy M87, I don't know which one that is, at nearly the speed of light. And that's incredible because particles aren't supposed to go near the speed of light. The jet is powered by a monstrous black hole that is estimated to have swallowed up matter equal to 2 billion times the sun's mass. It's unbelievable. Okay. So, and that, again, the Hubble Space Telescope. Thank you, Hubble, for all these pictures. All right, let's move to larger scale structures. We were talking about stars, weren't we? Now I'm going to go back in time a little bit here, so bear with me. It's not really time, but space. Here we are. I want to point something out to you. Said the brightest star out there was Sirius, but here's a Sirius A, and here is a Sirius B. What in the world is that about? Here we have a Procyon A, down here we have a Procyon B. Those are the only two I see like this here. What in the world is that talking about? These are not unitary stars like our sun. These are binary stars, meaning it's two stars that rotate around each other. Now here's the incredible thing. Those are the only two mentioned here, and the reason they're mentioned is that Procyon A is a main sequence star, and Procyon B is a white dwarf. And same thing with Sirius A and Sirius B. One of them's almost dead, and the other one's still alive, okay, you might say. Okay, let's go back where we were. Okay? Believe it or not, most stars out there in the sky are not unitary stars like our sun. Far more are binary stars. Two gravitationally bound stars together with each other. Most stars are in binary pairs. Ours is not. Now here's just a conjecture on my part, and I have absolutely nothing but gut feeling to support it. Okay, so I don't know that there's any real science behind this, but I do not see how planets around the binary stars, and most of them are binary stars, okay? Planets going around a binary star could ever support life as we know it. Because sometime you'll have twice the radiation, sometime you'll have half the radiation. I don't see how it could exist. I can see how they could exist in a thing, but how could they support life? If you think about how fragile life is on this planet, a little bit of change of temperature changes everything. You know? Everything. A little bit of change of radiation could change everything. So how in the world could a binary star support life as we know it? Now maybe there's life like we don't know it that it could support, but nothing like this. So all this conjecture about, oh, there's got to be more life out there somewhere in the universe, hey, can't be. I don't see how it could be around the binary star, and most of them are binary stars. Okay? I don't know how it could be with exactly our atmosphere. Okay? Because our atmosphere is perfect for us. Okay? We couldn't exist without it, with any changes in it. Okay? We are such a fragile little thing. A little bit further out or closer in, we'd probably burn up or freeze. Okay? So yeah, a little bit change of our tilt, and we might not exist then either. We have a perfect little system for life as we know it. Now maybe there's other forms of life out there, not as we know it. I can't argue that one, but life as we know it, we are such a fragile ecosystem, I don't know if we can do it. Okay, now beyond binary stars, you have what they call star clusters. This is tens. Now, I don't understand the slide, and I don't know if the book adds anything to it or not. In fact, I think something is wrong here. In the book it says, to groups of tens or hundreds of stars that have gravitational links and a common origin. And this says tens to hundreds of thousands or more gravitationally bound stars. That's 3 orders of magnitude different there. If you include thousands or don't include thousands, I think it's tens to hundreds of gravitationally bound stars. Those are stars clusters. Okay? The next sentence says, or to billions and billions of stars that form the basic unit of the universe, which is a galaxy. Okay? So these, which I don't think that 1,000 should be in there, but I don't know for sure. I think for right now I'm going to mark it out because it doesn't seem to match the book. So it's just tens to hundreds or more gravitationally bound stars. Okay? Not hundreds of thousands of gravitationally bound stars. They often share a common origin. Okay? Like one massive star, a mass nebula grouped together, and like that when we started about the Orion Nebula, it could 4,000 suns. Okay? Of course, they wouldn't all be the same size. Now, next beyond star clusters, though, are galaxies. Galaxy is the basic unit of the universe. Not a star, the galaxy. What are galaxies made up of? Billions and billions of gravitationally bound stars. Now we're talking billions, not hundreds and hundreds of thousands, billions of gravitationally bound stars. And guess what? There's even larger scales than that. There are clusters of galaxies, just like we have star clusters, you have galaxy clusters. And then you have superclusters of galaxies. And guess what? There's evidence there are billions and billions of galaxies, each containing billions and billions of stars. The numbers are so big I can't even see. I can't even begin to imagine what that's like. So, third rock from the sun, third speck of dust hanging out there somewhere. Okay, we are minuscule compared to the all of creation. It's just incredible. Now, let's get down to brass tacks here. And by the way, these closer looks are sometimes sort of fun, and this one is one of those. Extraterrestrials? I don't know if y'all are old enough to remember E.T. Phone Home, okay? He was supposed to be an extraterrestrial. This goes into it pretty much and says it's basically hard to believe they could ever exist. I mean, yeah, they could be out there, but not visiting, because you'd have to have lifetime after lifetime after lifetime just to travel the distance from one to another. It's unbelievable. Okay, so let's look at the Milky Way galaxy. That's where we live. Okay, and by the way, at the top of page 367 is the blurb on People Behind the Science, is what it's called. Jocelyn Susan Bell Burnell. At this time, it still has that she's still living, but she would now be up in her 70s, so she could easily still be living. And this was very positive, what they do here, but from what I understand, she definitely did not get the recognition she deserved. So I'm glad our book focused on her. Okay, so let's look at the Milky Way galaxy. That's where we live. Now, on a very dark night, a very clear dark night, when you're not in a bunch of light pollution, if you look up there and see this diffuse band that sort of goes across the sky there, and I have seen this on the farm, I'm not sure I've ever seen it in town. But you see this milky, and that's where it got its name. It looked like someone spilled milk across the celestial sphere, and because you can't distinguish stars, it's just a lighter patch there, and there's just billions and billions of stars behind those, and some of those are in galactic, I think they mean star clusters here, but anyway, that's the Milky Way. It looked like someone spilled milk in the sky, so they called it the Milky Way. Now, what is its structure? There's a galactic nucleus there, and that nucleus has to just be filled with lots and lots and lots and lots of stars. Okay, you would think they'd be close to each other. Well, they're closer than we are to our next nearest neighbor, maybe, but still they're so far apart they're not really interfering with each other. That makes up the galactic nucleus. Then around that is a rotating galactic disk of a diameter, okay, get this, 100,000 light years from end to end. So if E.T. came from anywhere in our galaxy, just maybe 10,000 light years away. That's pretty close, isn't it? Remember, a light year is around 6 trillion years, okay? Oh, 6 trillion miles, I'm sorry, times 10,000. Yeah, no one's going, no, just not going to happen, okay? Then, that rotating disk, outside of that, there's a spherical galactic halo that contains 150 or so globular clusters. Those are other clusters of stars that are not in the spiral galactic disk or in the central galactic nucleus. So here's the picture, approximately, of that. Now here's the actual night sky. This is taken probably somewhere out, probably in the desert, somewhere where it's very, very clear, and this is far brighter than I've ever seen it, but you see this band here, that's the Milky Way, okay? Or at least a little bit of it, okay? And you see, who knows how many stars are in that, you know, or in that. And this is just a little bit of it. I mean, just a tiny, tiny representation of it. Now, these out here could be in that galactic halo around the bands of the Milky Way. And there's lots of stars in that too, okay? Here's what it looks like. This is sort of a drawing now. Here is your galactic nucleus here, which we're representing here like this. And then you have the bands. Now this is looking down on it. This is if you turn this sideways. These are the bands here that are these bands. Now where are we? We're somewhere out here. We're outside the middle. We're not even in the middle of the galaxy. We're somewhere out there. And probably what we're seeing with the Milky Way is when you look this way or that way. We're not seeing any of that or this, probably, except some of those diffuse things. We're just probably looking at stars this way or that way. That's why I say we're only seeing a little bit of the Milky Way. Huh?
A tiny little portion.
Tiny little portion, okay? And yet billions of stars in that tiny little portion. It's just unbelievable, okay? Now, this is then the galactic halo, okay, with the globular clusters scattered around there. All part of the Milky Way galaxy. The main part is this part, okay? But around us are plenty more. Now, there's something about, and there's got to be in the physics of it, if you think about this, and we'll see this too, I can't remember if it's this chapter or the next chapter, our sun sits in the middle of rotating planets around it. And yet it has other objects above and below a lot like this. So this seems to be a shape common to nature, to have a central part, things in sort of a flat disk around it, and then things scattered above and below. That's exactly what we have here. Unbelievable numbers that we're dealing with. Okay. Now, we can go beyond the Milky Way to other galaxies. This is on page 368. Okay? All right. Our nearest neighbor, and this is called a local group, these are some dwarf galaxies. Now, we are 100,000 light years in our diameter. These are a mere 1,000 light years in diameter. So, if you put us next to them next to us, they are 1/100th the size of us in diameter. Number of stars would be far, far, far fewer than that. Our nearest dwarf is being disrupted already by the gravitational by the Milky Way. Now, there's some thought that we are actually going to suck some of those stars into, and they're going to join us in the Milky Way. I don't think it's anything close to happening now, and I don't think we'll really even notice it. But it seems to be being disrupted gravitationally. Maybe we'll just pull it apart so it no longer is a dwarf galaxy, it's just random stars out there, and we may suck some of them in, I don't know. But beyond that, now remember we're 100,000 light years across, okay? 2 million light years away from us, which is another 20 times that. So if 100 million light years across there, 20 times this, somewhere way out there is the Andromeda Galaxy, okay? 2 million light years away from us. Very similar to the Milky Way, okay? Now, it looks like us, it acts a lot like us. In fact, it seems like I've read somewhere it's a little bit larger than we are, okay? And there's some thought, well, if we're disrupting this dwarf galaxy, could Andromeda someday disrupt us? I don't think it's anything really to worry about. In fact, now this is hard to believe when you especially see those clusters and you think, how close those stars must be to each other. They're not. There's still a star here. The next star is so stinking far away. It's just amazing. That if the two galaxies ever were to collide, you might say, there's enough space there they can actually just move through each other before it. Now that is hard for me to believe. You would think at least the black holes would collide or something, but I don't even know how that would happen. But yes.
So does it have life?
What's that?
Does it have life?
Do they have life? We don't know, and we probably never will know. The odds, the percentages that the same type situation could exist somewhere among these billions and billions and billions and billions of stars, you would think has to be some star somewhere has similar planets, somewhat like us. Yeah, it could, but we don't know. And they're so stinking far apart, we'll never know. Okay, even if we could send out into space, it would take generations of people living in space to ever get there. And who knows if we can live in space? Because we need gravity. We need
Oxygen.
we'd have to produce our own, and we can do that. Nuclear submarines go under the water for months at a time, and they recirculate and break down and reproduce oxygen. Just recycle the oxygen. And I don't know exactly how they do that, but they do it. So I know it can happen, and it could be on a bigger scale in a spacecraft. But it would be generations, and how would people? I sort of hate to use the term, but evolve in that when you don't have. We wouldn't be the same. And could we ever come back and be the same? I don't think so. They've actually done a study. I can't remember the name of the astronaut, but one of the astronauts has been up into space for fairly long periods of time on the space station, places like that, has an identical twin brother who is not an astronaut. And they are studying those two like crazy to see if anything is changing to the one that's going up. And we're talking months. I guess a few have been up as long as a year or maybe more, but I don't know if any have been up that long. That's just minuscule as compared to generations up there. I don't know. I have my doubts. Okay. So, that's Andromeda. We don't know. Now, classification scheme. See, we can't even get across our galaxy. 100,000 light years. That's 2 million light years away. It takes light 2 million years to get from them to us, So, no, we'll never. We can't go anywhere close to speed of light. So again, guess what? Hubble is responsible for this. He classified these various galaxies as elliptical. That would be a lot like the planetary motion around the sun. Spiral, that's what we are. Those spirals, that goes around. Barred, those would be going out like this. And irregular, which could be anything. But those are the ones. I'm pretty sure are elliptical. Are spiral. I couldn't think of the name of it. Okay, yeah. There it says it. The nearest galaxy is Andromeda, about 2 million light years away. It's similar to Milky Way in size and shape, with about 100 billion stars, gas, and dust turning in a giant spiral pinwheel. Okay. Galaxies have other shapes, characteristics, blah, blah, blah. Okay. So, there is actually a Hubble Space Telescope picture of Andromeda. Much blown up. That's why it's a little on the fuzzy side, because it's taken from so far away, but blown up incredibly. Here's what they call the galactic nucleus. Okay. The spirals, you can't quite make them out, but you can see some of the distance in between them. And then the galactic, the halo around it, these globules around there. Okay. We talked about life of a star. Now let's talk about the life of a galaxy. Before we get there, there's this one mistakes and misunderstandings. Like I said, sometimes these are pretty good, sometimes they're a little on the weak side. This one is one that gets it down. Were any of you Star Trek fans? Okay, probably not. That was well before your time. I was my probably junior and senior years of college. I went to Georgia Tech, and they had the cafeteria there. I ate there some. My first 2 years, I usually ate with my brother at various places around. He couldn't stand the cafeteria food. But then after he graduated, and I was there for the next 2 years, I found out about this tea room, T for Georgia Tech, and it had a TV in it. I never watched TV when I was in college, ever. The only two things I remember watching my first 2 years was when Tech went to the NIT basketball tournament. I watched those 2 games, and that was the only television I watched then. But then my junior and senior years, I started going to the tea room for supper because they had a TV in there, and I ate from 5 to 6. Why? Because that's when Star Trek reruns were on. So I must have seen every show they ever produced, because I was only on TV for a year and a half or something like that, maybe longer, and once a week or something. So I watched it every night for a couple of years. And they had those communications. It is a myth that spaceships could have two-way communication. Radio waves travel at the speed of light, but the distances in space are huge. Here are the tables. Approximate time required for a radio signal to travel from Earth to the planet or to the place. Okay? Two-way communications would require twice the time. So if you were talking to Mars, our second closest planet neighbor, the Moon is our closest neighbor, Venus is the closest planet neighbor, Mars is the next closest. It would take 4.3 minutes for your signal to reach Mars. Now this is on average. There's sometimes Mars is further away when it's on the other side of the sun than what we are. So this is just average. To get two-way communication would be 8.6 minutes. So you ask a question, you wait 5 minutes, and then you get an answer. No, you wait 5 minutes, they hear your question, wait another 5 minutes, and then you hear their answer. Okay. Jupiter, which is the closest of the gas giants, 35 minutes for your radio signal to reach Jupiter on average. It could be, again, Jupiter could be almost twice as far away if it's on the other side of the sun. Okay? Saturn, 1.2 hours for one-way communication. Okay? Uranus, 2.6 hours. Okay? Neptune, 4 hours. And Pluto is not a planet anymore, but on average that would be 5.3 hours. If you're just talking across the Milky Way, now we are not, or if you remember, we wouldn't be talking across the Milky Way because there we are, or right there, across the Milky Way would be from there to there. So we would be somewhat less than this. But that'd be 100,000 years for your radio signal to get from you to the other side of the galaxy. Just our galaxy. To go to the, to go to Andromeda galaxy, 2 million years for one-way communication. 4 million years for it to get back. Okay, nah. There's not intergalactic communications. Not in the works. Okay? Now, let's look at the life of a galaxy. The current most popular theoretical explanation of how things happen was the Big Bang. Okay? This is not the television show, okay? This is science here. Surprisingly, that show has an awful lot of science in it. It has an awful lot of garbage in it too, but there is an incredible amount of science there. But the Big Bang Theory, best we can understand, is the universe came from some explosive beginning. Okay? All right. But what created the explosion? What happened before that? We don't know. It wouldn't have been the beginning if anything was before it. We don't know. But everything we do know and measure looks like it began that way. Here's the supporting evidence. Now this is very sketchy. Not sketchy in what is reality, but sketchy in what they tell us. Microwave background radiation. Okay? Now, what do we mean by that? Microwaves travel at the speed of light. Okay? And the background microwaves we can detect depends on how long ago we think those microwaves came from. It seems like there's some finite point back there that we don't see anything past that. But, on the other hand, what happened then may have already been past us now. I mean, this is hard to fathom. Large-scale expansion. Now, there are two things here that are really hard to understand for me. Well, the first one isn't that hard. It says large-scale expansion. Now, what that means is, and this was something else Hubble has done. Hubble's all over the place here. He detected data and then theorized based on that data that actually the universe is expanding. If there was a Big Bang, that makes sense. It would be expanding. Okay? Here's the part I can't understand, even begin to. Not only is it expanding, but it's accelerating in its expansion. And anything in physics that we know and understand is that the only way to have acceleration is if there's some net force. So if we're accelerating, that means there's some net force that's pushing us further and further apart. Accelerating meaning we're getting further apart at a faster rate. So not only are we expanding, but we're going at a faster rate. And I cannot begin to imagine what that force would be. Okay? The other, and we sort of hit on this a little bit, the relative abundances of the elements. Okay? According to what we know and understand, the relative abundance should center on iron, and everything over here get less and over here get less. And pretty rapidly so. But because we have a lot of things beyond iron at relatively large quantities, that means there had to have been something bigger than a supernova to produce that many. So Big Bang would account for that too. Now this leaves me hanging with very much to be desired. Diffuse cosmic background radiation that we've been detecting from the COBE spacecraft. And COBE stands for something, I can't remember what that stands for exactly. But I think cosmic is in the first part of that C. But this is, again, something like this, okay, that the stuff that we're reading and we're seeing from farther and further back in time indicates there's some limit back there. Okay, that's about all I can do. All right, what's the end then? If there's a Big Bang and we're expanding, are we going to expand forever and accelerate forever, getting further and further apart? Don't know. Okay? Or is it finally going to stop accelerating and reach an equilibrium and then maybe at some point start decelerating and then start coming back and then have a big crunch at the end? Guess what? Not going to happen in my lifetime. I'm not going to lose a lot of sleep trying to worry about it because we're still expanding at an accelerating rate. Who knows? I'm sure it's a very interesting scientific problem, but I don't have the aptitude to figure that one out. Now, here's an illustration of what's happening here. They use the illustration of making raisin bread and having the yeast in it, and the yeast is going to make the bread expand. And that's sort of what seems to be happening in our universe, is that things that were a certain distance apart, like the raisins here, 5 centimeters or 16 centimeters or 1 centimeter, after a while this became 2 and 10 and 32. They're expanding in every direction all the time. Okay. Now we're not doing that fast, but this would be the model of what's going on. What's happening is the rate of expansion is increasing. That doesn't happen with bread. You know, it expands maybe to start with some and then slows down and stops. You know, you just use up the yeast. Well, we haven't used up whatever is making us expand at an increasing acceleration. It's unfathomable to me. Okay. So this is what we think it's looking like. We think somewhere back there was a big bang, and then after a while the galaxies were out there. This only shows 4. There are actually billions of galaxies, billions upon billions, and they seem to be getting further and further apart. Are they ever going to come back together? We don't know. So far, no, they're expanding at an increasing acceleration. Whoa, can you believe it? There's the end of the chapter. Now, there are a couple of things here that I find very fascinating to read about. I don't know if you will or not, but they really seem. The first of these is on page 369, where the loaf was, that we were just seeing there. It's called dark energy. That's a strange terminology to me. But there's energy out there, okay, that we don't know what its source is or what it's doing, but we can measure that it's doing something. Energy is expended making this motion happen. That's a really fascinating little blurb to read. Might be a good paper topic if some of you are interested. Okay? On page 370, this thing about the expanding galaxy, Hubble's law is here. They write it down and they have you do a problem or two with it. You certainly are welcome to do those if you'd like. They just sort of threw it in at the end without any, I felt like they didn't tie it into the chapter that well, but you're certainly welcome to do that. Okay? But then on page 371, there's even a bigger blurb, a closer look, and this is on dark matter. Okay? And what they mean by this, we see stars. We know they're out there. They give off light. We can see them. Okay? We see planets, that's only close planets, because they reflect light from the sun. Now, some of those stars out there, with very careful measurements, you can see something is interrupting the light that's coming from that star to us every now and then. The best they can hypothesize is they have planets. And since our sun has planets, why wouldn't most of the other stars have planets? So they have been able to detect things like this. Okay? But when you do all these things that you can tell are there, then you look and you see so much more mass because of gravity and other things than you can account for. So this is mass that's out there, matter that's out there that doesn't give off light, that doesn't give any traces of itself. And if you read this, I think you'll see in here, there's some estimates that 10 times more matter in each galaxy than you can account for by the stars. 10 times! That's a lot of mass, but you can't detect where it's coming from. That's why they call it dark. You can't tell where it is. Okay. It's really a fascinating read. So I'll let you look at that. this thing of what the end is going to be. Your book has a figure 1421, at least 3 possible outcomes for our universe, given the universe's density, blah, blah, blah. And these 3 are illustrated here. Decelerating universes, coasting universes, and accelerating universes. Seems like to me most of the data suggests we're accelerating, but that seems hard to sustain. Okay, so I don't know. And then that's it. Now, I'm going to say this every chapter, so get used to it. Nothing replaces reading the text. Nothing. Okay? You've heard it before, right, Melanie? Patel? Okay. Nothing replaces reading the text. I'll let you in on a little secret. Not a very well kept secret. I've never had an astronomy course in my life. So when I first started teaching, I used to teach physics, which I had lots of physics courses. But then when they had us teach physical science, and I saw it had this whole big section on astronomy, I'd never had an astronomy course in my life. I took that first edition that I had of this book home with me every night and read ahead. Read from wherever I'd left off in class ahead, getting further than I knew we were going to do the next time we had it. I'd read it over and over again because some parts of it just didn't seem like we were talking today. You had azimuth angle measured from the South Pole. Later we're going to measure other angles. We're going to call them different names. It was all getting all crossed up in my mind. I read it over and over again, sorting it out and trying to get a better understanding. I may not have it all right. I probably don't. But this is the best of my understanding. But it took me reading these chapters over and over and over again to make sure I understood. So nothing replaces reading the chapter. Best done before we have it in class. Because I don't know how y'all felt today, but I can remember when I was in, say, calculus classes in college. I had never had any pre-calculus. I jumped right from advanced algebra and trig in high school into calculus 1 in college. And that was quite a transition. And I remember when the prof was up there talking, the professor up there talking, it was like blah, blah, blah. And I realized that if I read the chapter, read the section that I thought he was going to cover the night before, if I had the opportunity and did it, when I was reading it, it was blah, blah, blah. But the next day in class, when he went over it, some of the blah, blahs sort of fit together a little bit more. Whereas the days I didn't have a chance or didn't take the opportunity to read the night before, what he said in class was the blah, blah, and nothing tied it together, okay? So I think if this has been a little blah, blah, blah to you, reading the chapter ahead of time, then when we talk about it, hopefully it'll make more sense. Then when we do the lab, hopefully it'll make a little more sense. And then when you go back and study, hopefully the things will be falling together pretty well. So the better you can do this. So at the end of every chapter, but nothing replaces reading the chapter, there is a summary. Now this summary in this chapter is incredibly small for such a big chapter covering the whole universe. There's 3 equations mentioned. We're not really going to use these much at all. In fact, I don't even remember exactly where these showed up. I remember Hubble's law at the end there. Then there's a list of key terms, and this list is a little shorter than most chapters will be. But then comes applying the concepts. These are 50 multiple choice questions here. To me, this is the best thing to study for the test. Okay? Why? One reason, your tests are going to be mostly, not totally, but mostly multiple choice questions. Okay? And Patel and Melanie, you may remember the first test and the other one was mostly problem solving. This one is going to be multiple choice. So, not going to be the same questions, but the questions are going to cover the same material. So if you know these, you're going to be in a good shape to know those. Well, not only do they have the questions, they have the answers here. Now, I haven't checked every answer, so I can't swear to you all these answers are right, but I bet they are, because this is the 11th edition. They should have all the answers right by now, but they may have put some new questions in. But that's going to be the best thing. And 50 is maybe a little more than normal number of multiple choice, so that has quite a few of those here. Then there's questions for thought, and my word, they have 21 of these. And these are just thought questions, and you can find most of these in the reading. So this would not be a bad thing to look at either. Multiple choice questions, I think, are better, but the thought questions are pretty good. This is more than normal. Most chapters don't have 21. For further analysis, 5, that's about normal. You have some with 4, some with 6, whatever. There's a invitation to inquiry, which it's a pretty interesting little thing to read. And in fact, based on your reading of it, you might want to do a paper regarding it. Okay? And then you have the parallel exercises, which these are more like the examples in the book that mostly are drawn from physics and chemistry that we haven't had. So I would really, you might look at some of these and do some of them if you like, but that's not where I'd place my greater emphasis. Okay. Now, we're down to 5:20. Okay, we're supposed to go till 5:45. Before we decide what to do here, let's talk about next time, Thursday. We finished the chapter, so we're ready for the first test. That will be the last 30 minutes on Thursday. Okay? The previous 2 hours to that, or at least a portion of that, will be the lab from chapter 1. Okay? It's not a direct fit, but it's pretty close. Okay? And the 2 hours before that, we will definitely be in chapter 15. We won't get 15 covered. We'll just hit portions of it. But between those 2 hours and the next class, we'll probably get far enough along to have that lab. So the question is now what to do with the next 20 minutes we've got. And I really hate this because it was my oversight. I had fully intended to have the lab made up. I have the lab, but I don't have it run off. And what I can do is go down and see if I can find someone to unlock the copy room so I can make copies of the lab. And that way we can get started on the lab tonight. Won't get very much done, but get started on it so that then on Thursday we have a real good chance of finishing the lab in less than 2 hours. And if we finish the lab in less than 2 hours, you can start the test. And if we finish the test in less than 30 minutes, you can go home a little early. Okay? So the odds are if we go home early tonight, you're not going to be able to go home early, certainly not as early on Thursday. But now, so one option is me to go make copies of the lab. The second option would be going to get started on chapter 15. And that way we'll get a little bit covered tonight and then pick up on it when we come back on Thursday and then stop there, do the lab for chapter 14, and then do the test of 14. So those are the two options. I was just guessing y'all probably sick and tired of hearing me talk, so you might want to go and get started on the lab. What you think? Which would you rather, lab or chapter 15? Lab. That's what I would think too. So what I'm going to do is pause the